Hello, good morning, everyone. I think we have 17 right now. Okay, so maybe wait for another 5 minutes, yeah. Okay, for our friends to turn up, then we will start the session. Thank you. Hey, hello everyone. I think we have a good number to start now. All right. So yeah, again, good morning everyone. Hey, welcome to the second session here for this module. Okay. So yeah, I hope that everyone has already installed your jump tools here to your machine. Okay, so later after the morning break, we are going to use these jump tools, yeah, heavily, okay, for the hands-on exercise. Okay, and also today, please download the dataset. Okay, all dataset are in Jump. So later we will just use it, yeah, because it's quite a lot. I mean, quite some number of dataset. So please download them first, plug them to your desktop. So later we will just use it. Okay, the link is provided in e-learning portal. Okay, so please download the dataset accordingly, yeah. Okay, so last week we have learned about this EDA, the commonality analysis, and also the t-test, the green color part. Okay, so let me repeat again, just a quick reminder. Yeah. Okay, so we will use the one sample t-test, okay, when we have one group. Okay, when we have one group, we use one sample t-test. For example, you want to know whether the population mean is equals to 20 or smaller than 20 or greater than 20. So you have an amount and you want to know whether the population mean is equals to smaller than or greater than a specific value. You will use the one sample t-test. Okay, so if you have two groups, okay, if you have two groups, then we will use the two sample t-test. Okay, so if the two groups are independent, okay, for example, you want to compare the height or the weight of the male and female. Okay, there's no relationship between the two groups. They are different people, so we will use the independent sample t-test because the two groups are different. There's no relationship between the two groups. Okay, while if you want to um, compare the mean, the population mean between the two groups and the two groups are dependent. For example, you invent a medicine and you want to see whether the medicine is significant or not to the blood pressure value. Okay, so you measure the blood pressure value of the sample, okay, before they consume the medicine and after they consume the medicine. Okay, before and after they are the same person. Okay, there is a relationship between the two groups. So we will use the pair sample test. Okay, so last week we have learned how to form your own null and alternate hypothesis. It is very important because the tools will not able to help you to do so. You have to do it by yourself. Okay, the data scientist or the data analyst will need to do it by themselves. Okay, then the calculation wise can be done by the tools. Okay, so analysis again fall back to the data scientist or the data analyst. Okay, you will need to do the analysis by yourself. Okay, once you got all those value here from the tools or from the system. Okay, so okay, so last week we stopped on over the Python hands-on exercise. Let me go to this Python exercise. All right. So please please launch your Jupyter notebook. Okay, and we are going to do hands-on. I remember last week our friends has already asked like how we got a p-value, etc., etc. Right? So last week we learned about the analysis. Okay, so this week we learned about the hands-on part. All right, so how do we build the model, okay, and come up with the p-value, etc. Okay, so maybe a few minutes for you to boot up your Anaconda Jupyter notebook, and then we will start the hands-on exercise, okay, for the t-test, okay, to see how we can build our own model, okay, and then come up with the results and analyze them. Okay, just 1 or 2 minutes for you to boot up your Anaconda.
Didi, Didi, Didi. Oh, Didi, Didi. Mami apa? Apa nama? Mami WhatsApp kat Daddy. Daddy tolong buka download lah masuk dalam komputer.
Okay, so now let us start, yeah, the um, hands-on, okay, for the one sample t-test. Okay, so now let's see how we can do this in Python. Okay, then later we do it in Jump. Okay, then you can compare them. Okay, all right. So okay, so for the first example, we are going to use the brain size.csv, okay, which is this Excel file. Okay, I have put it upload it to the Google link, sorry, the Google Drive. Okay, so please download them accordingly from the Google Drive. Yeah. Okay. Okay, so for this brain size.csv, okay, we have the gender, the full skill IQ, the verbal IQ, the performance IQ, the weight and the height of the people, and then the brain, sorry, and then the MRI count. Okay, the MRI count. So okay, so first example, yeah, we look at the two sample t-test. Here you look at the two sample t-test. Okay, so first, the average mean of the population have the average verbal IQ score equals to 110. Okay, by the way, I think you will need to set your, as usual, yeah, a good practice. Okay, like we learned last week. Okay, you will need to set your directory. Okay, then only you can read in your Excel file accordingly. Okay, then only you can read in, yeah, your Excel file. Previously, we key in by ourselves. Okay, so now, okay, we need to export it or import it from the the Excel file. Okay, so first you need to set up your own directory. Here, let me remind you again, cd change directory. Okay, then you go to the folder that you save your data set. Let's say I save my data set in this folder. Okay, then I click on the directional bar, right click and copy. Okay, then I go back to the Jupyter Notebook, right click, paste. Okay, then I change the slash to the backslash. Okay, then you run it, then you will able to import your file later. Okay, we just need to do it once. Okay, just need to do it once, yeah. Okay. Okay, so for this example, we are going to see, okay, if the population mean, okay, is equal of the verbal IQ score, yeah, which is the verbal IQ, VIQ, okay, whether it is equals to 110 or not. Okay, whether it is equals to 110 or not. Okay, so meaning to say, we are going to look at this column, yellow color column, VIQ, okay, whether the population mean, yeah, population mean is equals to 110 or not. Okay, so first step again, okay, you will need to set up your own null and alternate hypothesis. Okay, null hypothesis is verbal IQ, the population mean of the verbal IQ score equals to 110. So this is the thing that we want to investigate. Okay, so alternate hypothesis will be population mean of the verbal IQ score not equals to 110. Okay, it is a complement for each other. Okay, so equals to 110, not equals to 110. All right. Okay, so all right. So now we'll proceed to the hands-on. Yeah, I mean to the coding. Okay, so for this example, okay, we are going to use SciPy. Okay, as I mentioned to you last week, okay, we heavily use this package, SciPy package, okay, for the statistical analysis. Okay, so we need to call this package. You need to just call it once, yeah. So over here, I put it in all the cell, okay, just in case in future you want to use it. Okay, so all right. First, okay, we will need to read in the CSV file, okay, because we are going to use this data set. So you're going to read in this CSV file, okay, read in this one. All right. So read CSV, brain size.csv. Okay, so we read in this file, yeah, and then I name it as data. You can name it as any name that you want. Okay, you can name it as any name that you want. The template is provided to you, but again, you will need to know, okay, where or which that you should change, okay, where to change and how to tune, how to modify, okay. So I name it as data for my print size.csv file. Okay, so after I got my data set into pandas data frame, which means I have rows and column, okay, then I will proceed to the statistical test. Okay, so since this is only one group, and we want to know whether it is equals to, greater than, or smaller than a specific value, okay, so we use the one sample t-test. Okay, so this is the package for the one sample t-test. Okay, t-test one sample. This one cannot change, yeah? Okay, data you can change to any name that you want, but this one, no. This is the name of the package. Okay, then, okay, you need to select the row, sorry, the column that you want. Okay, so for this one, I refer to this column only. Data, meaning the name of the data set, and I refer to only the yellow color column. I don't um, include, the remaining column. I only look at this column, verbal IQ. Okay, because that's my objective. Okay, so verbal IQ, I want to see whether it is equals to 110 or not. Okay, 110. Okay, so 110 over here, I put it here, then you can click the run button, you will get your result over here. Okay, so you will get your p-value equals to 0.053. Okay, 0.053. So since the p-value, again, the division rules that we have learned last week, okay, if the p-value is greater than 0.05, we have to accept the null hypothesis. Accept null hypothesis meaning we have to accept this one. Okay, meaning to say we agree with the claim saying that, okay, the population mean, okay, of the verbal IQ score is equals to 110. Okay, is equals to 110. So this is my claim. Okay, so I conclude that, okay, the population mean of the verbal IQ score is equals to 110. Okay, so this is the two-tailed test. Yeah. Okay, remember we have learned last week, if it is equal sign, then it is a two-tailed test. If it is a two test. If it is a smaller sign, smaller than sign, then it is a left-tailed test. Okay, so we have right-tailed test, left-tailed test, and equal sign. All right. So maybe you want to try, okay, for a few minutes, okay, on the two tests of the one sample t-test. Then we proceed to the right or the left two test. Receive one comment. You have an error to call your data set. Yeah, because you don't set the right directory. So you have to set your directory first because before you can call your data set. Yeah. So this is the way for you to set your directory. Okay, else you will not able to retrieve your data set. Okay, so let me demo again. Okay, how to set your directory. CD, change your directory. Okay, and then you go to the folder that you save your data set. Okay, then you click on the directional bar. Okay, then you right click and then you copy. Okay, then you go back to the Jupyter notebook. Okay, this one you have a space, yeah, space, and then you paste it. Okay, so after you paste it, then you have to change the slash to the backslash. Okay, then you just run it. Then you will get this. Okay, then you're able to import your file. Okay, you can try. Then you let me know.
Hi, Dr. Chiu. Is this class being recorded, Doctor?
Sorry?
Is this recorded, all of this session, this class?
Yeah, of course.
Oh,
Why?
okay, right, sure.
Yeah, the recording, I think Dr. Halim later will share with you. I'm not sure when, but I will let him know. Yeah. I think as usual, common practice, he will post it to the e-learning portal. Yeah, after the module. Thank you. so we move forward. Okay, so we have done the two-tier test, yeah? So now we will move to the right-tier test. Okay, this is one example, okay, for the right-tier test. Okay, so now if let's say you want to see if the average mean, okay, of the population visit have the average verbal IQ score, which is greater than 80, okay, greater than 80. So we only have one group and we want to see whether it is greater than 80 or not. Okay, and now we are going to focus on the full scale IQ score, which is this one, red color one. Okay, red color one. All right, so okay, so we will use the template that is provided to us. Okay, but you would, of course, you need to know where to modify. Okay, where should you modify? Okay, so the same thing you need to read in the data set. Okay, but if you already done just now, then no need lah. Yeah, but this is the template. Okay, so you can copy and use it. Okay, so the place that you will need to amend is over here. Okay, the M value, okay, which is this one. Okay, you want to see whether it is greater than which value. So your value can put over here. Okay, your value. All right. Then again, we use the one sample t-test. Okay, so now the same thing, yeah. Okay, but only this one we put it over here. But if you want to put an 80 inside this column, I mean this bracket is also possible. Okay, then of course you need to change your data set in future. If let's say you have different set of data, then you will need to change accordingly. But now, okay, I will use the same set. Okay, and then I only change this, yeah, the column. Previously it's a verbal IQ score, so now I change to the full scale IQ score. Okay, then we run it and you're able to get your result, p-value, okay, which is equals to 4.38 exponential negative 11. Okay, so what does it mean by this here? So this one, it means e negative 11, it means you have 10 0. So 0.000, you have 10 0 4 3 8 9, which means that it's a very, very small value, almost equals to 0. Okay? Very, very small value. So your conclusion is, since the p-value is smaller than 0.05, the division rules that we have learned last week, okay, so we reject the null hypothesis. Okay, we reject the null hypothesis, and then we, of course, if we say that we reject this one, meaning to say we agree with the alternate hypothesis. Okay, so we agree that, okay, the FSIQ score is greater than 80. Okay, so this is our conclusion. The full scale IQ score, the population mean of the full scale IQ score is greater than 80. Okay, so this is our conclusion. Okay, again, you will need to set up your own null and alternate hypothesis, yeah? Okay, so if you want to know whether it is greater than 80 or not, okay, so it will be your alternate hypothesis, greater than 80, because remember, okay, we have learned last week, the equal sign always belongs to the null hypothesis. Okay, so for this case, okay, your equal sign will be here. So when your alternate hypothesis is greater than 80, then your null hypothesis will be smaller than or equals to 80. Okay, so you run it and you got your conclusion over here. Okay, you can try. Then we will proceed to the left heel test. This is greater than, yeah, greater than, so it is a right heel test. You need to use the right template, yeah, in future. Okay, if it is greater than, then you use the right heel test punya template. Okay, if it is smaller than, then you use the left heel test template. Okay, so you try it, then you proceed. Okay, so now let us proceed to the left tail test, yeah? Okay, to the one sample t-test, left tail test. Okay, so now let's say if you want to check, okay, you want to verify, okay, if the average mean, okay, of the population, okay, the performance IQ score, whether it is smaller than 130. So now we look at another column, which is the performance IQ, the green color column. Okay, the green color column. So you need to modify your template accordingly. Okay, so now we want to see whether it is smaller than 130. So less than 130, it will be your alternate hypothesis because there's no equal, okay, the word equal over there. All right. So less than 130, okay, and then your null hypothesis will automatically be greater than or equals to 130. Okay. All right. Then okay, we proceed, yeah, to the modification. Okay, so the same thing. Okay, the only difference is over here you have to modify your m value. Okay, your m value is 130, so you have to modify your m value over here. Then you also need to modify the name of the column. Okay, now we refer to the performance IQ. Okay, not the other column anymore. Okay, then the remaining you can use the template. Okay, and you run it, you will get your p value, which is equals to 0.99. Okay, so since the p-value is greater than 0.05, again, the division rules that we have learned last week, okay, greater than 0.05, we have to accept the null hypothesis, meaning to say we accept this null hypothesis. Okay, so the population of the performance IQ is greater than or equals to 130. So this is our conclusion. Okay, so this is for the left tail test because over here is less than. Okay, you do a quick try, then we proceed to the two sample t-test.
Hi, Doctor. Hello.
Yes?
Hi. Yes.
Yeah.
After run this, my p value is different with from yours, and the result, your result is accept null hypothesis, but mine reject null hypothesis. Actually, what's the difference? Is it the difference from the data or what?
No. Do you use the right template? Because the right tail test template is this one, but then
Okay.
the left tail test template is this one. I suspect that you have used the right tail test punya template. You see, there's a difference over here. So I'm not sure you use the right template.
Okay. Right.
Okay, thank
I'm
you.
using the wrong template. Okay, so thank you.
I see. Okay, thank you. Okay, there's one question over here, not question, a feedback. Yeah, the p-value actually is okay because the difference is very, very small. Okay, because we use the different version. My one is the old version and yours one is the updated version. So there might be some tuning on the package wise. So it is okay because 0.99, yeah, no matter how we will have to accept the null hypothesis. Okay, but in jump tools later, you will see it will be round up to only 3 decimal point. Yeah, so sorry, 2 or 3 decimal point. Let me, yeah, I forgot which one. Later we will take a look. Oops, yeah, it's 3 decimal point. So yeah, different tools you will have different decimal places. Okay, thanks for the feedback.
Doctor,
Yep.
where there's a 1 minus result?
This one?
Yeah.
Because this is the other way around. So over here, so if you remember let me draw something. I open my pen. All right. So for two-tailed test, you remember like we have learned last week. Okay, this is the curve and we have two lines. Okay, so for the two-tailed test, we don't need to use that 1 minus or the greater than or smaller than because we have two-tailed tests. Okay, we have two tail. All right, so this is for the two-tailed test cases. Okay, so for this one-tailed test, okay, one we use this template smaller than the other one we use 1 minus is because okay we have one line, okay, and we have over here. So if your right-tailed test is over here, okay, so your left-tailed test will be 1 minus this one. Okay, so the remaining one will belongs to your left-tailed test when your result. Okay, so we will have one-tailed test. Sorry, we will have 1 minus. Okay, so why this one divided by 2 is because and then for the two-tailed test we don't divide by 2. Okay, because two-tailed test we have two tests, but one-tailed test, sorry, we have two tail. Okay, but one-tailed test we have only one tail, so we have to divide by 2 because we take into consideration only one tail. Okay, so this one divided by 2 is because of the tail. 1 minus is because of the direction. Okay, so later when you do the two sample t-test, you will notice that the result of the right t-test and the left t-test will give you the same conclusion. Okay, so for the two sample t-test, okay, you only need to use one test, either right t-test or left t-test, because they will give you the same conclusion. Okay, but I also demo to you both the right and the left t-test because different people write in different way. Okay, so if let's say you write something, over here is greater than, then you use the right t-test. If over here less than, then you use the left t-test. Okay, but then they will give you the same conclusion. Okay, for the two sample t-tests. Okay, later we will take a look on it. Okay,
All right. Okay, makes sense. Thank you.
okay, thank you. Okay, you have any more questions that you want to ask before we proceed to the pair sample t-test?
Hello?
Yep. Yes.
Just now you say VIQ is verbal IQ and
IQ.
the FS is full set. So P is
Full
what?
scale IQ.
Oh,
Performance
full
IQ.
scale.
The
Performance.
description is over here. Yeah.
Oh, okay, okay. Thank you, Doctor.
Thank you. Yep. So now we proceed to the pair sample t-test. Okay. So for the pair sample t-test, again, we will use it okay, when we have two groups and in the two groups are dependent. Yeah. Okay, there's a relationship between the two groups. Okay. So we start with the first example. Okay, so for this one, we are going to use the BIQ before and after dataset. This one. Before they attend the course, there's verbal IQ score, yellow, and after they attend the course, their verbal IQ score, green. Okay, so we have two groups. Okay, so we want to see whether the mean of the verbal IQ score for the population change after they attend the course for 1 year. So now we want to check whether the course is effective or not to the verbal IQ. Okay, whether the course is effective to the verbal IQ, whether it will affect the verbal IQ or not. Before the attended course and after the attended course is the same people. Okay, we are measuring the marks of the same people. So we are going to use the pair sample t-test. There is a relationship between the two groups. Okay, so we decide the test that you want to use and you draft your own null and alternate hypothesis. Yeah. Okay, so their claim, okay, not the same. The population mean of the verbal IQ score after and before are not equals to 0, meaning to say it's not the same. Okay, there is a difference between the score before they attend the course and after they attend the course. Okay, so automatically your null hypothesis will be the population mean after minus population mean before equals to 0, meaning to say the course will not affect the population mean. Okay, will not affect the population mean of the verbal IQ score. Okay, so we proceed to the codes. Okay, so again, we use the same package here. Okay, but the only difference is over here, we change to REL. Before this is one sample, right? So now we change to REL, the short form for relation, meaning to say there is a relationship between the two groups. Okay, so this one we will call out the package we use for pair sample t-test. All right. So over here, okay, we will put in the data set. Yeah, you pump in the data set first. Okay, previously we used the brain size.csv. Now we use the verbal IQ score before after.csv. Right. So now we look at the two column, the data after, meaning the column name after, data before, meaning the column name before. Data you can use any name that you want, you prefer. Okay, either A, B, C, C, D, E, or test or data, any name. Okay, so we look at these two columns. All right, so you run the test and you will get the p-value equals to 1.66 as exponential negative 33, meaning to say is 0.3201665. It's a very, very small value, almost equals to 0. Okay, so we have the p-value smaller than 0.05. We have to reject the null hypothesis. Okay, we have to reject the null hypothesis. Okay, reject the null hypothesis, meaning to say, we agree with the claim, saying that the cause is effective to the verbal IQ score, okay, of the participants. Okay, so from the two-tailed test, you can only know, okay, whether the score, okay, will be affected by the course or not. So if you attend the course, okay, your verbal IQ, your verbal IQ score will be affected. But from the two-tailed test, okay, you will not able to know either it's a good effect or it's a bad effect. We do not know, okay, whether it's a good effect or it's a bad effect. Is it improved after the attended course for 1 year, or it deteriorate, okay, after the attended course for 1 year? Okay, so it's a good effect or it's a bad effect. We don't know. We only know that it's a difference between the population mean, the score, verbal IQ score after the attended course. Okay, so that's the two-tailed test. We only know whether it is significant or not significant. So now we know that the course is significant to the verbal IQ score. But if you ask me whether it's a good effect or it's a bad effect, we don't know. Okay, so if we want to know whether it's a good effect or it's a bad effect, then we have to proceed to the left tail test or the right tail test. They will give you the same conclusion. Okay, because they are the complement of each other. Okay, like we have mentioned just now, is a one minus the other. Okay, so you will get back the same conclusion. Okay, so maybe you want to try the two tail test, then we proceed to the right and the left tail test. Yeah, one question over here. What is the meaning of the? Do we have a degree of freedom over here? Where do you see that? Yeah, because DF is a degree of freedom. I thought you have it in the jump tools only. Yeah. Do we have it over here? Yep. DF is a degree of freedom. Yeah, it's another stats that you will get. So yeah. Maybe it's the different versions that you have. Yep. The previous one we don't have. Yeah, but now maybe they have improved the values that you will get. So for all the statistical tools, you will get a lots of values when you run this, especially in jump. Later you will see you will get 20 something values. Okay, and same goes when you run SPSS, Minitab, all those, then yeah, you will get different amount and the values. So most importantly is you know which value that you should refer to, okay, and what is the meaning of that values. Okay, the meaning of that value. So if you get this value, so what does it mean? And what is the conclusions? Usually they will give you all the values, and from all those values those values are the values that you can derive from each other. For example, like the p value over here, you derive from your statistics, your t statistics value. You see, so they will give you all those original values, and then later maybe you learn regression, all those, then they will also output you all the statistical values that you get to derive your equations, but they also give you their regression equations. So yeah, um, it's important for you to know which one is the main one that you should pick and what is the meaning of that, and then go to the conclusions. All right, but thanks for letting me know, okay, that you have this DF value. Yeah, DF is the degree of freedom. Okay, let's move forward. Okay, so now we know that the course is effective to the verbal IQ score. Yeah. So we want to know whether it's a good effect or it's a bad effect, whether it improved after they attend the course for 1 year or it reduced after they attend the course for 1 year. Okay. So over here, okay. So now let's say, okay, different people write in different way, yeah. So if let's say I want to write in something like this, if let's say this is my belief, I believe that the verbal IQ score will improve after they attend the course for a year. Okay, after they attend the course for a year. So this is how I write. Verbal IQ score after is greater than the verbal IQ score before. After they attend the course, okay, the score become greater than the score before. Okay. So null hypothesis will automatically be smaller than or equals to. Okay, so we use this template, okay, the same template as the previous one, but over here we change to REL, yeah. From one sample we change to REL because we use different statistical tests. Okay, and you run the same template, you will get your result. Your p-value equals to 0.00. You have 330832. Okay, so meaning to say it's a very, very small value, almost equals to 0. Okay, so if that's the case, then we have to reject the null hypothesis. Okay, the division rule, yeah, we reject the null hypothesis. Okay, so we conclude that okay, the verbal IQ score after is greater than the verbal IQ score before. So meaning to say the course is effective. Okay, the course is effective because their score improved after they attend the course for 1 year. Okay, so it's a good effect. So now we know, okay, verbal IQ score after is greater than before. It's a good effect. Okay, so this is the right tilt test. Later we look at the left tilt test. Yeah, I got another questions here. You got the same conclusion, but the p-value, yeah, if the is the p-value different a lot or a little? If it is very little, then because of the version issues, I think same like our friends mentioned just now. Yep. Huge difference. Yeah. Actually, this one is 0.00006. So my one is 0.00. You have 32, 33 zero. So you might want to check. Okay, first you check the whether the equations, the template is the right one. Okay, the same one. Okay, if there's no, I believe there might be some typo or something. How about others? You got the same value or it's different? Same value. Okay, so maybe Afiq, you might want to change it. Thanks. Okay, thanks, Shah. Okay, so
Doctor,
Yep.
the case and the dataset used in the uh, one T, right? And the previous coding that we done is same cases and same data set, but why the p-value is different?
Sorry?
I mean, this one that we did, the current one till right, and also the previous one is the same case and the same data set, is it? But why the p-value is different?
Which one? The same data set, but the p-value is different.
Yeah. The currently is BIQ before and after, and previously was BIQ before and after as well.
Yeah, but the previous one is the 2-2 test. It's the
Two.
2-2 test. So of course the p-value have to be different. So previously it's a 2-2 test because this is our null and alternate hypothesis.
Uh-huh.
Okay, it's a equal sign. So we have to use the 2-2 test. So we run the 2-2 test template and we got the p-value 0.000, you have 320166. Okay,
Oh,
but
okay.
this one we can only know that the cost is significant to the verbal IQ score, but we don't know which one is bigger than which one. So
Mm-hmm.
if let's say we want to know, then we will proceed to the right to test.
Okay, I see.
So yeah, thanks.
Thank you.
Okay, so yeah, thanks for our friends too to share the p-value. Yep. So yeah, great. You all have the same p-value. Yeah, thank you. Okay, so from here we can know that the verbal IQ score after is greater than the verbal IQ score before. Okay, so now we proceed to the next one, okay, which is the left-to test. Okay, so different people write in different way. If let's say you think that the course is not effective to the verbal IQ score, okay, so if let's say that's your belief, then okay, you should uh try this method, which is the left-to test. If let's say this is your belief, you believe that the verbal IQ score after is smaller than the verbal IQ score before. So it means that if your belief, your verbal IQ score, you believe that the verbal IQ score after the attended course for 1 year, okay, will be smaller than the verbal IQ score before the attended course. Meaning to say it deteriorate after they attend the course for 1 year, getting worse. Okay, so in that if that's the case, then um yeah, this is your null and alternate hypothesis. Okay, so if over here is smaller than, then you should use the left to test template. And if it is greater than, then you use the right to test template. Okay, so over here you use the left to test template and you change your columns, okay, and your data set. Okay, and over here you change to REL. Just now is one sample, right? Now you change to REL. Okay, and you will get your p-value over here. Okay, and if the p-value is greater than 0.05, so addition rules, we have to accept the null hypothesis. Okay, we have to accept the null hypothesis, and then we conclude that the mean of the verbal IQ after the course, okay, is greater than the mean of the verbal IQ score before that than the course. So again, we get the same conclusion, the course is effective. Okay, so either you use right tail test or you use the left tail test. It depends on how you shape your null and alternate hypothesis. Okay, you will get the same conclusion. Okay, so thanks, Aina, for sharing your solutions. Yeah, thanks for trying as well. Okay, so I think we will proceed further since I think most of you are ready. Okay, you just modified from the previous template. Yeah. All right. So that's it about the pair sample t-test. Okay. So now you have learned about the sample t-test. Okay, how to do this in Python. Okay, and finally we will look at the independent sample t-test. Okay, we will look at the independent. We will use the independent sample t-test when you have two groups, and the two groups are independent. Okay, meaning to say there's no relationship between the two groups. Okay, for example, okay, we look back here to the brain size.csv file. Okay, so if let's say we want to compare the weight, okay, between the male and the female. Okay, we have two groups. Uh, okay, the weight of the male and the female. So now we look at the blue color one. Okay, so there is no relationship between the two groups, the male and the female. Okay, they are different from the others. Okay, so we were going to use the independent sample t-test. Okay, we will start with the two-tail test first. Okay, so for this, I will also introduce you one function, which is the extraction function. Okay, this is just I just tumpang this function over here lah to introduce to you. Okay, I think this is quite useful in case you have a data set and you want to extract some useful information. This is the function that you can use. Okay, so first we want to see whether the weight mean of the male and female are equal or not equal. Okay, so now hypothesis is equal to 0, meaning the weight of the male is the same with the weight of the female. There's no difference between the two groups. While alternate hypothesis, male minus female not equals to 0, meaning to say the population mean of the male is not equals to the population mean of the female. But from the two-tailed test, we can only know whether there is any difference between the weight of male and female. We do not know whether uh, the weight of male is greater than the weight of female, or the weight of female is greater than the weight of male. Okay, we don't know. We only know that if there's any difference. Okay, if you want to know further, then you proceed to the right or the left two test. Okay, else we will just stick to this. Okay, so first we read in the CSV file. Okay, and now we want to extract out the data. Yeah, we extract out the data. So this weight male, you can name it as any name that you want. Okay, so this one I name it as a weight male and female. Okay, any name that you want. Okay, then I extract the data column, name, gender. Okay, if the element is male, then I extract out the weight of the male. Okay, drop an A meaning I drop the empty cell. If the column is the gender is male, but there's no weight recorded, then I just drop the row. Okay, so I extract. This is for me to extract out the weight of the male. You see, over here, the weight is mixed around for the male and female. You see? So I want to extract out if it is male, then I extract out this 72.5. If it is male, then I extract out this 73.3. If it is male, then I extract out this 68.8. Okay, so the extraction function. Then I extract out the weight of the female. Okay, if it is female, then I extract out the weight. Okay, if it is female, again, then I extract out the weight. Okay, then I will have two columns, which is the weight of male and the weight of female. So you just put in into the package, then you will able to get your conclusion. Okay, so I run this template and I got the p-value, which is equals to 0.0000817. Okay, so if it is smaller than 0.05, we have to reject the null hypothesis. So it means that it is significant. So it means the weight of the male is different with the weight of the female. If there is a difference between the weight of the male and the weight of the female. But if you ask me whether the weight of the male is greater than the weight of female, or the weight of the female is greater than the weight of the male, there's no answer for this at this moment. Okay, so we only can conclude that there is a difference between the mean population mean weight of male and female. Okay, so you can have a quick try, then we proceed to the right and the left two test. Okay, there's one question. What is the difference between the t-test REL and INZ? Okay, so the t-test REL is for the pair sample t-test, the name of the package, the function. Okay, so it's for the pair sample t-test, okay, then you use REL. If it is a one sample t-test, then you use one SAMP, one sample. Okay, if it is an independent sample t-test, then you use the IND, okay, which is the short form for the independent. Okay, so you will have this different, the name of the package. So now we move to the right tilt test. Okay, so from here we have the conclusion saying that there is a difference between the weight of male and female, but we don't know whether the weight of the male is greater than the weight of the female and whether the weight of the female is greater than the weight of the male. That's another question. What is the meaning of equals the equal sign? Equal sign meanings if the data punya column, the gender punya column, if the elements is equals to this word male, then we extract out the weight. This is the meaning of this equal sign. So if the in this gender column, if the element is female, then we extract the weight. If the element is male, then we extract out the weight. Okay, thank you. Okay, thanks. So we move forward. Okay, if let's say, okay, we guess, okay, if let's say we guess the weight of the male is greater than the weight of the female. Okay, if let's say this is our belief, male is greater than female. Okay, then the null hypothesis is just the other way around. It is male is smaller than female. Okay, the weight of the male is smaller than the weight of the female. So over here is greater than, then we will use the right tilt test. Okay, we will use the right tilt test. Okay, so over here, the same template that we use, the same extraction function that we do. Okay, but now we use the right tilt test punya template. Okay. So just now REL we changed to IND, which means this is the package for the independent sample t-test. Okay, then we run the um, function, okay, and you will get the p-value equals to 0.0000408. Okay, which means we reject the null hypothesis. Okay, we reject the null hypothesis. It means that we agree with the claim. So we agree that the male is greater than the weight of the female. Okay, so the conclusion is the weight of the male, okay, is higher than the weight of the female. Okay, so this is the conclusion if you use the right tilt test. Okay, so we move to the last one, which is the left tilt test. Okay, so if let's say you form your null and alternate hypothesis like this, okay, different people write in different way. If let's say you believe that the weight of the male is smaller than the weight of the female, okay, then this is your null and alternate hypothesis. Okay, the weight of the male is smaller than the weight of the female. Okay, so if it is smaller then you should use the left tilt test punya template. Okay, so the same function, the same extraction function, same template, but you change your REL to IND, which means independent sample t-test. Okay. Then you run the template, you will get the p-value equals to 0.999, okay, which is greater than 0.05. Okay, again, if let's say it's greater than 0.05, we have to accept the null hypothesis. Okay, we have to accept the null hypothesis, and then we conclude that, okay, again, the same conclusion, yeah, the mean of the male, the weight of the male, okay, is greater than the mean weight of the female. Okay, so you get the same conclusion. All right, so we just need to do one test, either the left tail test or the right tail test. It depends on how you form your null and alternate hypothesis. You will get the same conclusion. Okay. All right, so if you have any questions that you want to ask for the test, the t-test up to this moment, before we proceed to the following demo, right? Okay, so next, this is just a few reminder for you, okay, for your future reference, yeah. Okay, so just now all the example that I show it to you, okay, if you notice that the two-tail test, yeah, all the two-tail tests, we have the p-value smaller than 0.05 and we reject the null hypothesis, is it? We reject the null hypothesis for the two-tail test, it means it is significant. So we proceed further. Okay, we proceed further. So for example, this case is significant, so it means there is a difference between the weight of the male and female. Then we proceed to the right or the left tail test to see if the weight of the male is greater than the weight of female, or if the weight of the female is greater than the weight of the male, right? So, for example, this case, okay, we know that the cost, okay, is effective for the verbal IQ score from the two-tail test. Then we proceed to see whether it's a good effect or it's a bad effect. Okay, so what if it is not significant for your two-tail test? For example, this case, you want to compare the mean weight, the mean population mean, yeah, of the verbal IQ score and the FSIQ score, whether they are the same or not. Okay, you have verbal IQ score punya column and the full scale IQ score punya column. So now I want to compare the weight, sorry, the mean between the verbal IQ score and the full scale IQ score. Okay, so I start with the two-tail test first, yeah. Okay, I start with the two-tail test. Okay, if over here, okay, the same step that we use, the same template, okay, the same step. Okay, so you put it in and you get the p-value 0.83, you see, which is greater than 0.05. Okay, greater than 0.05, it means we have to accept the null hypothesis. We cannot reject the null hypothesis. So it means that there is no difference between the population mean of the verbal IQ score and the full scale IQ score. There's no difference. Okay, so this is the example, okay, for the two-tail test with a p-value greater than 0.05. If you got this kind of result in future, then no need to proceed with the one-tail test. Okay, so because they already told you there is no difference between the population means of verbal IQ score and the FSIQ score. There's no difference. They're the same, the population mean. Okay, so if you proceed to the one-tail test, then you know you will get an invalid answer because there's you cannot investigate anymore whether this one is greater than this one or this one is greater than this one, because from the two-tail test they already told you that they are the same. There is no difference. Okay, there's no difference. So no need. You just stop over here and we conclude that the population mean of the verbal IQ score and the FSIQ score are the same. Just that. Okay, so that's our conclusion. Okay, if you accidentally perform the one-tail test, okay, let's see what will happen. Yeah. So we use the same template, same method. Yeah. okay, as previous. Okay, so now you run the right tilt test. Okay, if let's say you want to check, yeah, whether the FSIQ score is greater than the verbal IQ score or not. Okay, if the FSIQ score is greater than the verbal IQ score. Okay, so over here, okay, we will use the right tilt test because it's a greater than. When you run the template, you get the p-value 0.42. Okay, which means p-value is greater than 0.05. Greater than 0.05, we have to accept the null hypothesis. So from the right tilt test, we conclude that the FSIQ score is smaller. Okay, you conclude the FSIQ score is smaller. Okay, so you check again the left tilt test. Okay, if you believe that the FSIQ score is smaller than the verbal IQ score, yeah. Okay, so you run the same template, okay, as the previous one, okay, and you got the p-value equals to 0.58, which means the p-value is greater than 0.05. So if the p-value is greater than 0.05, it means that we have to accept the null hypothesis. We accept the null hypothesis, it means that the FSIQ score is greater now. You see? So just now, right tilt test, you already conclude that the FSIQ score is smaller. But if you run the left tilt test, you get the FSIQ score is greater. You see? So you get an invalid result. Okay? So this, I mean, this is just to demo to you. Okay, if you got p-value greater than 0.05 for your two tilt test, then no need to perform the one tilt test. Just stop there and you conclude that there is no difference between the two groups. Just that. Okay? So if you proceed further, then you will get an invalid result. Okay? So this is just a reminder lah, yeah, for your future reference. Okay, so the time now 10:39. I think we proceed for one example, then we proceed with the short break, yeah. Okay, so you have any question, can let me know, yeah. All right, so up to this point, okay, up to this point we have learned about all the EDA techniques and also the part one of the CDA techniques. Okay, so you have learned all these small components, and how are we going to apply it to a real world data set? How? Okay, so that's the main goal for the module. Okay, so I hope that all of you can learn how to apply, okay, the small parts or the theories that you have learned to a real world data set, which is the data set that you have in your hand. Okay, so I will show you this example, okay, to see how we can combine the analysis from EDA, which is the exploratory data analysis, and the CDA confirmatory data analysis. Okay. So for example, this dataset plating.csv, it is a Excel file. Okay, so for this example, we are not going to try, but I will just walk you through how to apply. Okay, because I think this is very important. The final goal is you need to learn how to apply them. Okay, so for this example, we have two vector, which is the wave current and the wave age. Okay, you have two factor. Okay, and you have the lots, which is a good lot or the bad lot. Okay, so we want to determine the cost of the low yielding lot at the plating module. Okay, so you have a plating module. Okay, there is a low yielding lot detected. Okay, so you want to know what is the reason, okay, for these low yielding lots. Okay, and you want to solve it, and you want to bring the process back to normal. So you have there are two things that they suspect, which is the wave current, whether it is because of the current, the ampere is being set too high, or it's because of the wave age, because of the apparatus is too old. Okay, the age is too old already, so it affect the performance of the line, you see, the module. So let us investigate. Okay, so first we will this is optional actually. Okay, this is optional. So you can get the summary, okay, of your data set by using the describe function. You can know how many rows you have, okay, what is the mean, standard deviation, and then the quartile performance, okay, of your data set. This is optional. Okay, so this is how our data set looks like. Okay, so I pump it into the pandas data frame to the nice row and column. Okay, so okay, so now we have two factor, yeah, that we suspect. Is it because of the age or is it because of the current? Okay, so first we look at the age, yeah. We look at the age. Okay, so I want to plot a chart that this the age, okay, the babe punya age versus the date. Okay, I want to look at the good lots and the bad lot. Okay, so we have learned about this during the visualization part. Okay, if you want to plot age versus date, which means you have two continuous variable, okay, we will need to use a scatter plot. Okay, so you yourself as a data scientist or data analyst, you will need to decide what is the visualization or what is the charts that you want to plot. Okay, so for our case, we will use the scatter plot because we have both continuous variable. Okay, you decide to use a scatter plot. So we use the template that you have learned last week. Okay, the scatter plot punya template. Okay, and you plot. Okay, you plot a chart. Okay, so this is how you plot the scatter plot. Okay, you select the right colors, the right marker, etc., etc. You label them accordingly. We have learned all this last week. Okay, so now you apply them. Okay, so this is the graph that the scatter plot that you have plot based on the data set that you have. Okay, so from here you can see that actually there is no commonality being observed from the charts, you see, because you can see that this is the age. Yeah? If it is new, the apparatus is new, there are some bad lots produced. Okay, if the apparatus is old, there are also some bad lots being produced. So there is no commonality being observed. There's no signal being observed that the age actually affect the good lots and the bad lots. You see, because okay, because they are the same. You see, because they are the same. If it is new, there is some bad lot. If there's old, there are also some bad lots. So there's no significant difference, or maybe it's not significant enough for us to see the commonality over here. You see? So from here, we actually can conclude that there is no commonality being observed. So age is actually not a determining factor that cause the bad lot. Okay, age is not the significant factor from here. Okay, so if you talk about the real world implementation, okay, one chart, of course, definitely is not sufficient to, to support your findings, you see. If you want to tell people that, okay, we can now ignore the age, we proceed to the next factor, you see. So it's not convincing by using only one chart, okay. So to make it more convincing, maybe you want to plot another chart, which is the box plot. Okay, because you have lot quality, which is the good or the bad, versus the age over here. Okay, so when you plot, we use the same template. Yeah, we have learned last week how to plot a box plot. We label it accordingly. We put the colors that we prefer, etc., etc. Okay, so this is the box plot that we get. You see, so from the box plot again, we see that there is no commonality being observed because you can see that the distribution spread widely from the new apparatus to the old apparatus. You see, so actually there's no significant difference. As she mentioned that the bad lot happens when the apparatus is very new or the apparatus is very old. You see, so there's no significant difference being found. You see, so from here we conclude that there is no commonality being observed. Okay, for this factor, which is the age of the babe, which is the apparatus they use for plating. Okay, so This is about the EDA, the exploratory data analysis. Okay, this is the conclusion that we get. Of course, when you talk about real-world implementation, one EDA itself is not sufficient. So you have to prove further by using CDA, confirmatory data analysis. So we have also learned about this just now, how to conduct the t-test by using Python. Okay, so if let's say we want to know whether the age is significant or not for the good lot and the bad lot. Okay, so now we have two groups, the population mean of the bad lot and the population mean of the good lot. Okay, so from here, okay, we have two groups, and if the two group is independent, there is no relationship between the two groups. They are different groups. Okay, so you have to decide. Okay, as a data scientist or data analyst, you have to decide what is the test that you're going to use. Okay, so we apply the knowledge that we have learned last week. Okay, if we have two groups and there is no relationship between the two groups, we will use the independent sample t-test. Okay, we will use the independent sample t-test. So this is the independent sample t-test punya template. Okay, and we have the we start with the two-tail test first. Okay, we start with the two-tail test. So you run the template and you get the p-value 0.47, which means your p-value is greater than 0.05. Okay, so we accept the null hypothesis, which means we accept this one, and we conclude that actually the wave H is not significant for this point. Okay, so again, we prove that the H is not the determining factor. Okay, the H is not the determining factor. So we have the same conclusion for all the three tests that we have done. Okay, so we conclude that now the engineer can just ignore the factor wave H. Okay, because this is not the main factor for the low yielding lots. Okay, so this is for the first factor that we investigate. So they can ignore this factor. Okay, but we have another factor, which is the wave current. Okay, the wave current. So now we want to check whether the current is significant or not. Okay, whether the current is significant or not. Okay, to the low yielding lots. Okay, it is significant or not significant. Okay, so from here, we can see that over here, okay, we use the same methods here. So now we want to plot a scatter plot because we have the current, which is the continuous variable, and the date, which is also the continuous variable. When we have two continuous variable, you have to select scatter plot. So you have decide the plots that you want to use and you proceed to perform the plottings. Okay, so from here, you can clearly see that, okay, we use the same template, yeah, what we have learned last week. Okay, from here, you can clearly see that actually there is a commonality being observed, you see. The bad lot is being generated when the wave current, the amperes, yeah, is being set below 20, you see. All the bad lots happens when the current is being set below 20. Okay, so when it is below 20, then it produces the bad current. So this is the commonality that we observe. You see, from this date to this date, the wave current is being set below 20 and it generates bad lot. So from here, the engineer can actually have a very clear direction to check on these dates why the wave current is being set below 20. Is it because of the electric issues or because of the human factor, etc., etc.? So they can check accordingly. Okay, but again, when you talk about real-world implementation, one chart is not sufficient to support your justification. So we proceed further, okay, to plot a box plot. Okay, so we use the same template that we learned last week. And from here, you can actually see that this is the bad lot box plot. Okay, and you can see that it happens when the current is set below 20, you see. All bad lot happens when the current is being set below 20. So from here again, we get the same conclusion. Okay, when the ampere is being set below 20, then it generates bad lots. So again, a very clear direction for the engineers to investigate why the current is being set below 20 during these days. Okay, so of course, only exploratory data analysis itself is not sufficient. Okay, you have to proceed with the confirmatory data analysis to further support your findings. Okay, so we have two groups. Okay, and the two groups are independent. We will use the independent sample t-test. Okay, so we start with the two-tail test first. Okay, before we proceed to the right or the left tail test. Okay, so we use the independent sample t-test. You use the template that you have used just now. Okay, and from here, you can actually notice that your p-value is 0.00. You have 130140. Okay, so it means that it's a very, very small value. Okay, a very small value. So from here, it is smaller than 0.05. So we already can conclude that there is a significant difference between the group population mean, okay, for the base current. So we can conclude that the current, okay, is the significant factor that affect the good lots and the bad lot. Okay, so we move on. Okay, if let's say we stop at this moment, I mean, we can also stop over here and we just conclude that, okay, the current, the base current is significant. So the engineer should proceed to investigate this factor, which is the base current. But just in case, if you want to know if the base current of, the base current of the good lot is greater than the base current of the bad lot. Okay, which one is greater than which one? The current of the good lot is better than the current of the bad lot, or the current of the bad lot is greater than the current of the good lot. So we will proceed to the right or the left tail test. Just use one, you will get the same conclusion. If I believe that the current of the good lot is greater than the current of the bad lot, I will use the right tail test punya template and you get the p-value 0.00. You have 14.0 p-value, so we reject the null hypothesis. When we reject the null hypothesis, meaning to say that we agree with the alternate hypothesis, so we conclude that the population mean of the base current for the good lot is greater than the population mean of the bad lot. So again, it support our findings for our EDA. Okay, our exploratory data analysis, okay, which means that if you have a greater base current, then you will generate good lots, but if the current is small, then you will generate a bad lot, which means that below 20, then it is a bad lot. So again, it support our findings. Okay, so if you use the latitude test, you will get the same conclusion. If you believe that the current of the good lot is smaller than the current of the bad lot, so you use the left tail test template. Okay, so you run the template and you get your p-value equals to 1.0, which means that you accept the null hypothesis. So you accept your null hypothesis. Again, you have the same conclusion. The current of the good, the base current, okay, of the good lot is greater than the current of the bad lot. So again, you get the same conclusion. It supports your EDA findings. Okay, so the final conclusion: all the bad lots will process when the current is set less than 20 amperes. Okay, and you got the specific date from our EDA analysis just now. Okay, so it's a very straightforward, we already simplify it to the engineers and they can just, go to this root cause and find out why this happens and solve it and bring the process back to normal. Okay, so this is how you apply the knowledge that you have learned previously. Okay, you combine the exploratory data analysis and the confirmatory data analysis to a real world example. Okay, so far you have any questions that you want to ask before we proceed to the break?
Doctor, I have question.
Yep. Yes.
From the data, from the result of scatter plot and then the box plot, we already know is below 20 yield the bad lot, right? And then we further test with the independent sympathy test. So in real world, do we have to do all these three or we can choose either one?
Okay, so thanks for your question. So yeah, I mean if let's say you talk about experiment, paper-based experiment, then you might want to choose only one, you see. But if let's say we talk about the real world implementation, because it's the real world example that I have here when I previously worked in a multinational company. So only one exam one analysis is not sufficient to support the implementation actions. So the manager will not going to do anything if let's say we have only one analysis. So we have to support it because for them time is money. If you go to the wrong direction or you have the wrong interpretation, then it is a huge loss for the department or for the company. So they want to be very, very sure for them is above 90%. They want to be very, very sure. So when you talk about this, show me more, example, convince the engineer so that they will listen to you because we are just a statistician, you see. Of course, their experience, as an engineer, etc., they will have or our manager, they will have a greater experience than us. So how are we going to convince people, our audience? Okay, it's like you sell a product, you see, people is more experienced than us. So how are we going to use data, or the techniques to convince people so that they can buy our idea, buy our product, you see? So that's why uh for real world example, real world scenarios, we need at least two. So either we use one EDA. CDA actually is a must because EDA actually is based on the experience of the people. So maybe when you first time look at this one, or maybe you look at this scatter plot, you will have no idea. What does it mean? I have this scatter plot, so is it significant? There's any commonality being observed, etc. But when the time goes, you look at more scatter plot, more charts, etc. Then you know, okay, one glance, and we know, okay, this is significant, this is not significant, etc. You see? So this is also based on the personal experience as well. So to the real implementation, I guess you will need to have at least one EDA and then one support from your CDA at least. Okay, then only you can convince people to buy your idea and apply it or really implement it. Yeah. Okay.
Okay, thanks, Doctor.
Thank you. Any more questions that you want to ask? All right. If you have no questions, then I think we stop over here for 20 minutes, quick break. Okay, then we will proceed after 20 minutes. Thank you. Hey, hello everyone. Welcome back. Okay, so I think we will proceed further. Okay, for the hands-on, okay, on jump. So today we will have theory, hands-on, theory, hands-on. Is a mixture lah, yeah, for each other. Okay, the hands-on and also the theory. All right, so we have learned how to do one sample t-test and two sample t-tests by using Python. So now we will proceed to see how we can do this in jump, okay, in jump tools. All right, so I hope your jump tools are ready, okay, in your machine. Okay, so this is how your jumps looks like when you first launch it. Okay, maybe just a few minutes for you to boot up your jump tools before we proceed further. Hmm. So for your jump tools, it will be empty lah, because over here the left hand side is the recent file that you open. So I simply open a few just now, so it will be listed over here. So if you don't open any file yet, then it should be an empty one lah. Okay, so your right hand side will be your active window. Your active window, for example, um later when you open a few data set, etc., and then your how to say, your results. Here you have run, and then you got numerous results. Then it will be shown over here, the active windows that you have. Now I didn't open any data set, any windows, so it will be empty. Okay, so as a quick start, okay, just to introduce you the basic function of jump. Okay, um I would like you to open maybe one data set, and then we go through it. Okay, just a quick intro to the basic function. Actually, there are a lots of function for jump tools, very famous statistical tools. Okay, that's been widely used in the industry. Okay, so yeah, just I just introduce you a few basic one because of the time constraint. Okay, so a basic one, then later you might want to explore it accordingly. Okay, so let's open one data set. Yeah, we can click this open button. Okay, then you go to the place that you save all your data set. All this data set has been uploaded to the Google Drive. Yeah, so um, you can open it. Okay, you can open it. Then you choose the try this C example. This one. Click, and then you open it. Okay. So just to introduce you a few functions. This one, the just now the Python code has already been made available in e-learning portal. Okay, please feel free to take a look on it. And then this jump lab here that we're going to do now is also already up to the portal. Okay, you can download it accordingly lah. Okay, so now just a few introduction about the basic function of jump. Okay, so over here the left hand side, yeah. Okay, left hand side, you can actually see how many columns and how many rows that you have. Okay, for now I have only two columns, but in future, if let's say your data set is very huge, then you might want to take a look on this. How many columns that you have over here, two, and how many rows you have over here is 60. Okay, so I have two columns, 60 row. Okay. All right. Then okay, so remember that we have learned previously about the type of variable that we have. Okay, so from here you can actually see easily see the type of data that you have. Okay, so for example, the blue color one is the continuous variable. Okay, continuous variable are numbers. Okay, then the red color one is the nominal variable. Okay, we have learned this last week, yeah? Okay, so we have nominal variable, okay, which is the categorical variable. Okay, so you can actually change it accordingly based on your preference. Okay, so you can click on this variable and then you right click. You can go to column info. So from here, you can actually edit the details. You can actually edit the details of the data that you have. Okay, so from here, for example, the column name, okay, then the data type. Okay, your data type, for example, numeric is the numbers, character is the categorical variable. So these are the two that we have been using. Okay, the basic one. Okay, so if let's say you want to put you want to set it as a numbers continuous variable, then we use the numeric, and then we choose continuous. Then you click OK. Then it will be blue color, which means that is a continuous variable. Okay, so if you right click column info, if you want to change to a categorical variable, you can do so. You just click the drop down button, choose character, and then you choose nominal. You click OK, you see that it will change to red color, which means that is a nominal variable, categorical variable. Okay, let me change back this one. Column info, numeric, and then it's a continuous variable for temperature. Okay, so it's back to blue color, which is the continuous variable. Okay, so from here, the same thing, yeah, you can do for the other variables, yeah, that you have. Okay, so if you right click this one, beside column info, you can also see other function. Let me introduce one or two commonly used one. The first one is the label unlabel. Okay, if you click this label unlabel, you can see it over here. This one, it means the variable is being labeled. Okay, the variable is being labeled. So it means later when you plot a scatter plot, so you have dot, 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 all those markers, right? So if you have this label, then it means that it will label the temperature beside the dot. Okay, some of you might want to have the dots label, then you can use this function. Okay, else you can just right click and label it. You see, it disappeared, so it won't appear in your scatter plot later. Okay, so this is the meaning of the label unlabel. Okay, and then another function, hide unhide function. So hide unhide function, it means you can hide it from your graphics. Okay, you can hide the data from your graphic. For example, if you have a sensitive data, okay, for example, salary. Okay, you plot a chart that include the salary of the employee. Okay, and you do not want people to know that. Okay, so you can hide them up. So you can use this hide unhide function. Okay, so another function is the exclude and exclude function. So exclude and exclude function is you want to exclude this column or this variable from your experiment or from your analysis. Then you can use this exclude and exclude function. Okay, so hide and hide, it will still be taken into consideration in your analysis. You won't exclude them, you just hide them. Okay, but exclude and exclude, you will already exclude them from your analysis. So when you calculate maybe mean, mode, median, etc., then it won't be taken into consideration that specific variable. Okay, so these are a few basic one that I would like to introduce to you. And also, you can actually set the decimal places for the variable. Okay, for example, you can see over here temperature, right? You have 0.5, 0.4, 3.9, and then no decimal place, 0.4, etc., etc. So if let's say we want to standardize them into the same decimal places, you can right click, then you click column info. Okay, then you choose the format, yeah? You go to this fixed decimal place, fixed decimal point, and you can insert how many decimal place that you want. how many. If let's say I want to have 2 decimal point, then I choose 2. I click OK, then it will be changed to 2 decimal place already for all the elements, all the component. Okay, so this is the basic function of jump. Okay, any questions that you want to ask before we proceed to the manually input of the data set? Okay, so I believe it's a straightforward one. Okay, so now if this one is we open it from a data set, a data source, right? If let's say if we want to input some data into a new data table, okay, we can do so. Okay, if let's say you want to create, let's say in your Jump Lab page number 3, okay, you can create that table, okay, in a new data table. So you click File, you go to New, and you choose Data Table. Okay, you choose data table, then you will have a new data table over here. Okay, if let's say you want to change the title of your jump data table, you can click here. Double click, then you can rename try or whatever. Then enter, you see, it has been renamed to the name that you want. Okay, then from here you can simply add rows and columns. Okay, yeah, many ways that you can do. So I just demo the ordinary way. Okay, but there are many ways actually. Yeah. Okay, so ordinary way is you can go to the rows. Okay, then you can add rows. So how many rows that we want to add? Let's say I add 3 rows. Then I click OK. Okay, so I have already successfully created 3 rows. Okay, if I want to create column, okay, I want to add new column. Okay, I can go to maybe columns, new column. Okay, then I want to add, let's say 3 as well. Click OK. Then I will have another 3 columns. So in total, I will have 4 columns. Okay, so now let's input our data. Yeah. So if you look at the data table in page 3 of the Jump Lab menu, okay, you have lot, name, date, and yield. Okay, so let's input for the lot function, the variable. Okay, so for lot variable, okay, you can click on the column 1, this one, and then you right click column info. Okay, so let's say I change to lot. All right, then for lot actually is a nominal variable. It's not continuous variable, it's nominal variable. It's a red color icon. So I change over here to character, nominal variable. I click OK. See, it has been changed to red color. Okay, then I start to insert the element 1, 2, 2, 2, 3, 3, 3. Okay, then it has been done. I mean the first column. Okay, you have input it correctly. Okay, then we proceed to the next column. If let's say now I want to insert the name of the people. Okay, so you click on column 2, 1, right click, column info. Now you can change the column name to name. And then for name is character, nominal variable. Okay, then you click OK. See, it has been changed to red color. Now you insert name, Peter, Jane, Jack. Okay, so you have your name here. Okay, this is the nominal variable. And then you have date, third column. Click the column 2, right click, column info, then you put in date as the name of the column. Okay, then change the data type to date is a continuous variable, but then you need to select your format. What is the format of the date time that you want? Right, you click this and then you choose date time. I select one format that I want, then I click OK. Okay. Then you can insert your date. It will change to help you to change to the format accordingly. Okay, it will change to the format that you choose just now accordingly. You see? So this is the insert of the date data. Okay, and finally, if let's say you want to input the data for yield, okay, right click, column info, then you choose yield. Yield is a continuous variable, but if let's say I want to fix the decimal point for this variable, I can do so. Click the fix decimal point. Then I insert, I only want to have 2 decimal point. Okay. Then I can start to insert my value 11, 12, 13.4. You see? So it will be automatically changed to 2 decimal point. Okay. So this is how we insert the data manually. If let's say you want, usually we will import it from Excel file or data table. Okay, but this is just in case in future you want to insert something manually, then you can do so. All right. So this is the basic function for jump tools. And we proceed to the one sample t-test example. So far, you have any questions that you want to ask before we proceed to the example? You know, yeah? All right, if no, then we proceed to the first example, okay, which is this one. Okay, so let's say an analysis shows that the employee in a company with 50 employee, they send 67 message per day. Yeah. So you want to know, okay, whether the population mean is 67 is greater than 67. Okay, this is the objective. Greater than 67 or not. Okay, so you want to know whether the employee in the company send greater than 67 or not per day. You see? So you randomly pick some sample and you ask them how many message they sent in the previous day. Okay, so can we conclude that the mean number is greater than 67 or not? Okay, so how do we do this in JUMP? Okay, previously we have learned how we do this in Python, but now let's try in JUMP tools. Okay, then you can compare which one that you prefer more. Okay, so we open the data set, open, you choose the one t-test example, you open, okay, that you get the data over here. Okay, so now I'm going to demo to you how do we do one sample t-test in JUMP. Okay, in JUMP tools. So you click analyze, then you click distribution. Okay, then you click the mean, click, yeah. Then you click this Y column. You put it into Y variable. Then it will come to this. Okay, click mean, click Y, then it will appear over here. Then you click OK. Okay, then not yet, yeah, not yet. You click this triangle, you see the red color triangle. Okay, you click this red color triangle, you choose the test mean. Choose this test mean, yeah? Okay, click the test mean. Oops, I clicked the wrong one, sorry. Repeat again, distribution, put in the mean, click OK. Red color triangle, and choose the test mean, yeah? Okay, so over here, how many message they send is 67. So I put in 67 over here because I want to know whether it's greater than 67 or not. So I put in over here, then I click OK. Then you will get this tons of values. So refer to the value that you should refer to. Okay, so we will refer, let me put into proper writing for you. Okay, so again, first you will need to set your own null and alternate hypothesis. Okay, you have learned this last week. Okay, how to set the hypothesis if it is greater than 67. Okay, so H1 is greater than 67. And the null hypothesis, of course, it will be automatically be smaller than or equals to 67. Okay. So this is the screenshot that I provide to you for your future reference. In case if you forgot, then you can refer to this one. Okay. So these are the data or the results that you get, okay, that you will get from JUMP tools. Okay, so how to interpret them? Okay, so first you have set your own null and alternate hypothesis, and you will get your p-value over here. Okay, so p-value, if let's say over here is a right tilde test greater than, then you refer to this one, greater than sign. So this is your p-value that you should refer to. Okay, if over here your alternate hypothesis is a smaller than, then is a left tilde test, then you refer to this one, the third, the last one. Okay, and if it is an equal sign, then you refer to the second one, this one. Okay, 67. Okay, so you have the equal sign greater than or smaller than. Over here, we want to see whether it is greater than 67 or not. So we refer to this one, 0.19. Okay, 0.19. So it is greater than 67. So for this case, greater than 0.05 p-value, we cannot reject the null hypothesis. Okay, we cannot reject the null hypothesis. Okay, so it means that we have to agree with this. So our conclusion is, okay, we conclude that the mean number is not greater than 67. Okay, it is not greater than 67. All right. So this is our conclusion. Okay, so this is the difference when you use the Python and also the JUMP tools. Okay, then you can compare yourself and then choose the one that you prefer. Okay, so far you have any questions that you want to ask for the one sample t-test before we proceed to the next one, which is the pair sample t-test. Okay, so if there's no questions, then we proceed to the pair sample t-test. Okay, for the pair sample t-test, we will use it when you have two groups and if the two groups are dependent, meaning there is a relationship between the two groups. Okay, for example, okay, the first one, the doctor want to know whether the medicine is effective or not for the blood pressure value. Okay, so the doctor want to know whether the medicine is efficient or it will affect the blood pressure value of the patient. So he select a few sample. Okay, and B is before they eat the medicine, they measure the blood pressure value, and after they consume the medicine, again they measure their blood pressure value. So there is a relationship between the two groups. So we will use the pair sample t-test. Okay, so how do we do this in JUMP to get our p-value? Okay, so let's open the data set in JUMP tools. Open pair t-test example. We click open. Okay, you will get before and after. Before is the blood pressure value before they consume the medicine. After is the blood pressure value after they consume the medicine. Okay, so you have before and after. All right, so for pair sample t-test, the first thing that we need to do is you want to find the difference between the two groups. Okay, the difference between the two groups, yeah? Okay, so difference between the two groups, first you need to create a new column so that you can calculate the difference between the two groups. Okay, so double click this column or you want to add column, okay, based on your preference. Okay, so from here, right click, you put in formula, yeah, you're going to put in formula. formula. Okay. So you click after, you click minus, you click before. So I want to use the column after minus before. I want to get the difference between the two groups. Okay, so this is what I do. After minus before, then I click OK. Okay, you will get the difference between the two groups in this column number 3. All right.
Can you repeat, Doctor?
Oh, yeah, sure. Let me repeat. Okay. Okay, you create a new, okay, so let's say if you want to create a column here, double click on this new column. All right. Then we right click. Then we choose the formula. Okay. Then we click after. Then it will appear over here. Then we click minus. Then it will appear over here. Then you click before. Then it will appear over here. Then we click OK. See? Then we will get the difference between the two groups over here. Okay, now we have the active window, you see? Then this one, it will appear over here. These are all the active windows that you have. Yeah? Okay. So we have create a new columns, okay, with the data over here. All right. So now we click, we are going to do pet number t-test, yeah? So that is step 1. Step 2, you click analyze, the same thing, analyze, and then we click the distribution. Okay, so now you put in your column 4 or column 3, okay, to this Y column. You click column 3, you click Y column, then your column 3 will appear here. Okay, you click column 3 and then you click Y, then it will appear here. Then you click OK. Not yet, yeah? Okay, not yet. Okay, you click the red color triangle. Then we choose the test mean. Okay, we choose the test mean. Don't need to do anything, yeah? Choose test mean, then we click OK. This one will remain as 0 because we want to know whether it is equals to 0 or not. Okay, then you click OK. Okay, then you will get your p-value over here. Okay. Right, so let me put in proper writing for you. Okay, this is for your future reference, the screenshot, right? Okay, so first you form your own null and alternate hypothesis. The tools were not able to help you to do so, so you yourself will need to form your own null and alternate hypothesis. Okay, so null hypothesis, mu A minus mu B equals to 0, meaning to A is after, yeah, B is before. Okay, so before they eat the medicine and after they consume the medicine, their blood pressure value are the same. Okay, or their blood pressure value are not the same. So you remember the equal sign always belongs to the null hypothesis. Okay, so from here okay, so this is equal sign, yeah? Equal sign we will refer to the first value, this one. Okay, we will refer to the first value over here. All right, so this is equal sign, this is greater sign, this is smaller sign, yeah? So if we have a great equal sign over here, we refer to the first p-value. So we got 0.23, okay, which is greater than 0.05. So we conclude that the new medicine will not affect the blood pressure value. So it is not significant. The medicine is not significant to the blood pressure value. Okay, for the population mean, yeah. Okay, it is not significant to the blood pressure value. So this is the conclusion. Okay, so form your own hypothesis, look at the suitable value, and make the conclusion. Okay, so this is for the hair sample t-test. So please try this example. Okay, I would like you to try this example because only you try, then you know how much that you understand, okay, about this test. Okay, in case if you have any questions, then you can ask. Okay, so try to do this example in Jump and see what is the conclusion that you get. Okay, so now we look at this example. We see how we can do this in jump. Yeah. So for this example, they want to see whether the environment will affect the arrows that is being made by the people or not. Okay, whether the environment will affect the performance of the people. All right. So first, we open the data set. This is try this B. All right. So first step is we find the difference formula. Okay, quiet minus loud. Okay. Then from here, analyze distribution. We put in column Y, we click OK. Okay. Red color triangle, test mean, remain as 0, click OK. You see? Then you will get your values, P values over here. Let me put in proper writing. Okay, so this is your null and alternate hypothesis. You want to see if there's any difference between the performance of the people when they do the task in the quiet environment versus the arrows when they do the task in the loud environment. Okay, so when you do a two-tailed test, you will notice that the p-value is 0.02. So it means that it is significant. So it means the environment, okay, will affect the performance of the people. Okay, the environment will affect the performance of the people. But if you ask me whether they will perform better in a quiet environment or in the loud environment, we have no answer for that because this is a two-tailed test. Okay, so we can conclude that it is significant. So the environment will affect the performance, okay, of the people when they conduct the task. Okay, so if let's say you want to see if they can perform better when they do the task in a quiet environment, or they perform better when they do the task in the loud environment. Okay, so um, the arrows made in the quiet environment is smaller than the arrows made in the loud environment. Okay, so these are the arrows, yeah, arrows made here. Yeah? So quiet environment smaller than loud environment. Okay, so quiet environment, okay, it means the arrows made, yeah, in the quiet environment smaller than loud environment. So it means they perform better in a quiet environment because they make less arrow. Okay, so maybe the environment is quiet, then less disturbance, so they perform better. Okay, so for this case, we need to refer to the third one, which is the last one, which is smaller than, because over here is smaller than sign. Okay, so smaller than, so we have 0.0103. So it means that smaller than 0.05. So we have to reject the null hypothesis. Okay, so we reject null hypothesis, meaning to say we agree with this. So we agree that the errors being made by the participants be in the quiet environment is smaller than the errors being made by the participant when they conduct the task in a loud environment. So quiet is smaller than loud. Okay, so this is our conclusion for this exercise. All right, so that's it about the pair sample t-test, and we're going to move forward to the independent sample t-test. Okay, no question, yeah? I hope everyone can get the same conclusion, right? So for the two independent sample t-test, okay, two sample independent sample t-test, we will use it when you have two groups, and if the two groups are independent, there is no relationship between each other. For example, okay, if let's say Mr. Simpson believed that the smell of the fresh baking will encourage the customer to buy from his bakery. So he don't know whether his belief is right or wrong, you see. So he want to investigate his belief. So he record the sales 10 days when the window is open. So he opened the window and he record down the sales for the 10 days. So meaning to say when the window is open, then maybe the fresh baking smell fly out from the window, then it encourage people to buy. Okay, then when the window is closed, okay, when the window are closed, you know, the smell cannot fly out from the window, then yeah, maybe because of that, then yeah, his belief is less people will buy. So let's see if his belief is right or wrong. You see, so this is the null and alternate hypothesis that we have. Meal open greater than meal close, meaning to say the sales of the bakery when the window is open is greater than the sales when the window is closed. This is his belief. He believed that the sales when the window is open is greater than the sales when the window are closed. Okay, so let's see how we can do this in Jump Tools. We open the independent t-test example. Okay, so now I'm going to introduce you the stack function, yeah, in Jump. I think this is very useful to you for your future, okay, for your pre-processing wise. Okay, so in order for you to conduct the independent sample t-test, okay, you will need to have one nominal variable and one continuous variable, which means you need to have one red and one blue variable. But over here, you can see that you have both blue colors. You see, you have both blue colors. So in this case, we cannot, you see, we cannot do independent sample t-test. So we need to pre-process our data. Okay, we need to pre-process our data before we can move forward. Okay, so we have to stack the table. Okay, table. We stack the table. Now we want to merge. Okay, we want to merge the sales when the window is closed and when the window are open. So we use the stack function. We stack the table. So you highlight both and then we stack the column. Here we stack the column. All right. Then you click OK. You see, now we have two columns. We stack the table window close and window open as one label, and the data we have all the sales. Okay, we stack them up together. You click OK, then you will get this two column. You see? You see, now you will get one red and one blue for you to proceed with the independent sample t-test. Okay. All right, so we move forward. Okay, so for this example, okay, you click analyze. Okay, then you click fit y by x. No more distribution. Yeah, you click fit y by x. Click. Then remember the blue color, which is the continuous variable, always belongs to y. And the red color always belongs to x. Remember, yeah, continuous variable always belongs to your y variable, yeah? Okay, then you click OK. Not yet, yeah? Okay. Then you click the red color triangle and you choose the pull t-test over here. You will get your p-value over here. Okay? All right, so let me put in proper writing for you. Again, the screenshot is for your future reference, yeah? Okay? Okay, so this is our null and alternate hypothesis. Okay, and since this is a greater than sign, okay, this is a greater than sign, so we will need to refer to the just one, the greater than sign. Okay, the greater than sign. So you will get the p-value, okay, which is 0.0086, which is smaller than 0.05. Okay, so it is smaller than 0.05. We have to reject the null hypothesis. When we reject null hypothesis, it means that we agree with the alternate hypothesis. So it means the mu, okay, the sales when the window is open is greater than the sales when the window are closed. Okay, so this is our conclusion. Okay, so we conclude that the sales when the window is open is greater than the sales when the window is closed. Okay, so it means that the fresh baking smell will encourage people to buy from Mr. Simpson's bakery. Okay, so his belief is right. Okay, so this is the conclusion for our 2 sample independent t-tests. Okay, so you might want to have a quick try for this exercise, okay, before we proceed to the next statistical test. If you have any question, then can let me know. Okay, so let me demo to you for this example. Okay, so open, try this C. Okay, so for this example, okay, the same thing. Okay, now we have one red and one blue variable. So you can proceed, okay, to the independent sample t-test, yeah. All right, so analyze fit y by x. Remember, the blue color always belongs to y. The red color always belongs to x. Then you click OK. Right? Red color triangle, and you choose the Q test. Then you will get your p-value over here. Let me put in proper writing for you. All right. So this is your null and alternate hypothesis. You just want to see if the population mean of the lot 1, okay, is equals to the population mean of lot 2. Okay, because this is an equal sign, so we refer to the first one, okay, for the equal sign, 0.1973. Okay, 0.1973. So since the p-value is greater than 0.05 division rule, we cannot reject the null hypothesis. Okay, so since we cannot reject the null hypothesis, so we have to accept this one. So it means that the population mean of mu1 is equals to mu2. So there is no difference in the population mean temperature for the two selected lots. Okay, so that is the conclusion that we get. All right. So that's
Doctor,
it about, yep.
I would like to
Yes.
ask, just now, this one, we did not reject the null hypothesis, so means no different. For example, if the value is less than 0.05, and then means that it's not same, so then we can refer to bigger than or smaller than.
Then we can proceed to the right or the left field test.
Oh, okay, okay.
Okay, thank you. Any more questions that you want to ask before we proceed to the ANOVA test? All right. So if no questions, then we proceed to the ANOVA test. Yeah. Okay. So for ANOVA test, we have two main type, which is the one-way ANOVA and the two-way ANOVA test. So again, when to use which is very important knowledge that we have to know, because the data scientists or the data analysts themselves will need to decide here when to use which one. Okay, so ANOVA test, okay, for one-way ANOVA test, we will use it when you have more than two groups. Just now you have one group, you use one sample t-test. You have two groups, you use two sample t-tests. And if you have more than two groups, then you will use the one-way ANOVA test. Okay, so for one-way ANOVA test, okay, so this later we look at more example. Okay, we look at more example. Okay, so these are the standard template for the one-way ANOVA test. Okay, now hypothesis, there is no significant difference between the group mean score. Okay, alternate hypothesis, there is a significant difference between the group mean score. So this is for one-way ANOVA test. When you have more than two groups, then you use the one-way ANOVA test. And you have more than one factor, because just now we look at only one factor, either is the age, the salary, the weight, the height, etc., etc. Okay, so now if let's say we only look at one factor, we look at more than one factor, for example gender and also age, instead of one factor, then you will need to use the two-way ANOVA test. Okay, so if you have only one factor, then we use one-way ANOVA test. You have two factor, then you use two-way ANOVA test. Okay, so this is just for your reference, and the ANOVA analysis of variance. Okay, we use the F distribution. Okay, so this is how we this is kind of like the standard way that we form our null and alternate hypothesis. Okay, so now hypothesis is mu1 equals to mu2 equals to mu3 if you have three groups. You can have 3, 4, 5, 6, 7, 8. It depends on how many groups that you have. Okay, so if you have three groups, this is how you write your null hypothesis. You can write in words, you can write in symbols. As long as you can understand it, then it should be fine. Okay, so for the first example, mu1 equals to mu2 equals to mu3, meaning the population mean for population 1 is equals to 2 is equals to 3, meaning there is no difference between the three groups. Okay, so if let's say alternate hypothesis, okay, it will be there is a significant difference between the group mean score, meaning to say at least one of the mu is different from the others. For example, maybe mu2 is different from mu3 and mu1, or maybe mu1 is different with the value of mu2 or mu3. Okay, so this is the meaning of your alternate hypothesis. Okay, we look at more example, yeah, to have a clearer idea. Okay. For example, this case. If let's say a manufacturing plant, they want to determine the best material to build their product for a customer. So they have different vendor, okay, that provide them the material. They don't know they should buy from who. Okay. So they want to investigate whether the vendor is significant or not to the quality of the product. Okay, they want to know whether the vendor is significant to the quality of the product. If let's say the vendor is not significant to the quality of the product, then they just simply buy from the vendor that can give them the cheapest price. Okay, but if let's say it's significant, then they have to select carefully lah. Okay, so first they will need to form their own null and alternate hypothesis. If let's say there are three vendor, vendor A, vendor B, and vendor C, and they want to check the steadiness of the metals, okay, to represent the quality lah, the quality of the product. Okay, so for this one, the first one, okay, null hypothesis mu A equals to mu B equals to mu C. It means, okay, the population mean of A. Okay, the population mean of for the quality of the product for vendor A is the same with the vendor B is the same with the vendor C. So meaning to say the vendor is not significant to the quality of the product. Okay, this is the first one. Okay, so alternate hypothesis will just be the other way around. Not all the mu are the same. So meaning to say at least one of them are different. So meaning to for alternate hypothesis, it means the vendor is significant to the quality of the product. Okay, so at least one of the vendor have the different quality from the other two. Okay, so we look at the p-value. Okay, you do the test and you look at the p-value. If the p-value is 0.25, which is greater than 0.05, we cannot reject the null hypothesis. Okay, we cannot reject the null hypothesis. So meaning to say we cannot reject this one. So we agree with the null hypothesis, meaning to say the vendor is not significant to the quality of the product. So they can just buy from the vendor that can give them the cheapest price because the vendor is not significant. Okay, the vendor is not significant, so okay, they can just buy from any vendor that can give them the cheapest price. Okay, this is the conclusion. Okay, so this is the example for one-way ANOVA test. Another example, if let's say you have 4 auto body shops, okay, and of course the shop will claim that they have a prompt repair time. Okay, so you want to check, okay, you want to check if the shop is significant or not to the repair time. Okay, if it's not significant, then we just go to any shops that can give us the cheapest price, right? So what we do is first you set up the null and alternate hypothesis. Now we have 4 shop. Shop A, shop B, shop C, and shop D. And these are the with repair time. Okay, the population mean of the repair time. Okay, so from here we can see that if let's say we agree with the null hypothesis, it means that the shop is not significant to the repair time. So you can just go to any shop because they will be almost the same time repair time. Okay, while if you agree with the alternate hypothesis, it means that not all the meal are the same. At least one of them are different from the others. Okay, so we use the ANOVA test because we have more than 2 groups, so we use the ANOVA test. And since the p-value is smaller than 0.05, we have to reject the null hypothesis. Okay, we reject this one null hypothesis. Okay, so it means that there is a difference. Okay, between there is a difference in the repair time. So we agree with this one. At least one of them are different. So from this experiment, we know that okay the shop is actually significant to the repair time. Okay, is significant to the repair time. So if let's say you want to know further which one is the significant one or which one is the different one, then you use back the t-test that we have learned just now in the morning and also last week. Okay, so this is how you do the one-way ANOVA test. So let's see how we can do this in JUMP tools. How we conduct the one-way ANOVA test in JUMP tools. Okay, for example, this case. If you have 3 clubs, club 1, club 2, and club 3, okay, for the golf clubs, okay, and you want to know whether the club is significant or not to the distance of the golf ball. Okay, you want to know whether the club is significant or not to the distance of the golf ball. Okay, if it's not significant, then you can simply choose one. Okay, if it is significant, then you cannot simply, I mean, you need to find out the significant one. Okay, so how we can do this in JUMP? Okay, so we open the data set, open one-way ANOVA test, you click open. Okay, so now we have club 1, club 2, and club 3. This is the distance of the golf ball. Okay, so again, when we want to use one-way ANOVA test, you need to have one red and one blue, which means you need to have one continuous variable and one nominal variable. Okay, but over here we have 3 blue. Okay, we have 3 blue, which means it's not we cannot do this. Okay, we cannot do this for one-way ANOVA test. Okay, so we have to do some pre-processing, okay, in order for us to achieve one red and one blue. Okay, so stack the table first. Okay, stack the table. Okay, table, stack. All right, so we highlight all this. Okay, so you click the stack column, you see? So now we have one red and one blue already. Okay, then you click OK. You see? So now you have one red and one blue. So we are ready to do the one-way ANOVA test. Okay, analyze, fit y by x. Okay, we click. Remember, yeah, the blue color always belongs to y, the red color always belongs to x. Okay, the red color always belongs to x, the blue color always belongs to y. Then we click OK. Not yet, yeah? Okay, red color triangle. Choose ANOVA test. Okay, then you will get your p-value, overall p-value over here. Okay, so overall p-value, we look at the overall p-value. Let me put in proper writing for you. Okay, this is the screenshot for your future reference. Okay, so from the overall p-value, we can see that it is smaller than 0.05. So we have to reject the null hypothesis. Okay, so we reject the null hypothesis, meaning to say we agree with this one. So not all the mu are the same, meaning to say the cloud is significant to the distance of the golf ball. Okay, the cloud is significant to the distance of the golf ball. At least one of these mu are different from the others. Okay, either mu1 is different with mu2 or mu3. So who is the different one? We don't know. So ANOVA test actually will stop here and we conclude that, okay, now club is significant to the distance of the golf ball. Okay, so this is our conclusion. But if let's say you want to know further, which one is the significant one? Club 1, club 2, or club 3? Which one? Which one is the different one? mu1 is different with mu2 and mu3, or mu2 is different with mu1 and mu3, or mu3 is different with mu1 or mu2. So which one? Who is the different one? For this case, we need to proceed with the t-test. Okay, we have to proceed with the t-test. Right, so we go back to the triangle. You click compare means and you choose the t-test. So we compare one by one. So you will get the order difference report, okay, from here. You see? So what does it mean? Okay. From here, you compare club 1 and club 3. Okay, club 1 and club 3 values. Significant, it means different. So from the experiment, they told you that mu1 is different with mu3. Mu1 is different with mu2. And mu2 is the same with mu3 because it's not significant, is it? Mu2 and mu3 is not significant. So mu2 is not is the same, okay, with mu3. Okay, not significant, it means there's no difference. Okay, so who is the different one? Okay, when you compare 1 and 3, they are different. You compare 2 and 3, there is no difference. So meaning to say the value of mu2 and mu3 are the same, while the different one is mu1. So we can conclude that mu1 is the significant one, where mu1 value is different with mu2 and mu3. Okay, so this is the final conclusion that we have. Okay. All right. So let's try this. If you have 4 brands, brand A, B, C, and D, okay, let's see if the brand of the battery is significant or not to the lifetime of the battery. If it is not significant, then we just choose the cheapest one. Okay, so let's see. Let's do this in jump and we see whether it is significant or not significant. Okay, you can try. Okay, thank you. We have seen that our friends has done the experiment. So let's see. Okay, let's do it together. Okay, to see if it is greater than 0.05. Try this one example. Okay, first we stack the table. Okay, because we need one red and one blue. Okay, so we click OK. Now we get one red and one blue, and we use fit y by x. Remember, the blue color always belongs to y. The red color always belongs to x. Then we click OK. Okay. Red color triangle, we choose ANOVA test, and you can see the overall p-value is greater than 0.05. Yes, so friends, you got the right answer where it is greater than 0.05. We cannot reject the null hypothesis, so it is not significant. So we can say that the the brand is actually not significant to the lifetime of the battery. So for this case, okay, they can just choose any brand that is the cheapest one. Okay, so this is the example for one-way ANOVA test. Do you have any questions before we proceed to the two-way ANOVA test? Okay, so we have no question here for the one-way ANOVA test. So we proceed to the two-way ANOVA test. We will use the two-way ANOVA test when you have more than one factor. Okay, for example, previously we look at only one factor, either age or either gender. So now if let's say we want to look at two factors together, age and also gender, so we will use the two-way ANOVA test. Okay, we will use the two-way ANOVA test. So um, for the two-way ANOVA test, you will have 6 hypotheses instead of 2. Okay, you will have 6 hypotheses instead of 2 hypotheses. Okay, so this is how you form your null hypothesis. So the first null hypothesis is regarding your first factor, which is the age. And the second null hypothesis is regarding your second factor, which is the gender. And the third null hypothesis is regarding your third factor. Sorry, we have no third factor, there's only 2 factor. Okay, the third null hypothesis is regarding the interaction effect, okay, of the factors where, okay, there is a relationship or there is no relationship between the 2 factor. Okay, so null hypothesis, it mentioned that there is no relationship between the age and the gender. Okay, there is no relationship between the age and also the gender. All right, so for the okay, for this example, okay, alternate hypothesis is just the other way around. Oh, there's a question. So what does it mean by the interaction effect? So interaction effect, it means let me explain maybe in the general term. So in layman term, okay, the interaction effect, it means interaction effect, it means for example, we go and see doctor. If you have a flu and you go and see doctor, and doctor give you a medicine which is a round shape and a square shape. Okay, so if you eat only the round shape, it won't cure your flu. If you eat only the round shape or only the square shape, it won't cure your flu. But if you eat both the round shape and the square shape, then they will have interaction effect and the effect will be able to cure your flu. That's the meaning of the interaction effect, meaning to say that is an interaction between the 2 factor. Okay, so this is the meaning of this interaction effect. So for this example, okay, we look at one example for the two-way ANOVA test. Okay, for the two-way ANOVA test, maybe you want to spend 1 minute to read this, then I will summarize this for you. Okay, so we look at this example. Okay, so this example, we have two factors, yeah? We have the flooring and we also have the stripping, you see? So previously we look at only one factor, but now we look at both factors. So for this case, we have to use the two-way ANOVA test. Okay, so for this example, okay, the flooring and the stripping, okay, we will use it to guide the AGV, which is the automated guide vehicle. Automated guide vehicle meaning there's no people driving. Okay, it is guided by the stripping and it walks on the floor. Okay, so they want to know whether the stripping and the flooring is significant or not to the distance that the vehicles can travel before it goes out of control. Meaning to say, it will follow the street until some time, then it go out of the path. Okay, so they want to know whether the stripping and the flooring is effective or not, or is significant or not, or it will affect the distance of the AGV or not. Okay. So first, you will need to set up your null and alternate hypothesis. First null hypothesis is regarding your first factor, which is the stripping, meaning to say stripping is not significant. Yeah, stripping is not significant to the distance of the AGV travel. Okay, next, the second null hypothesis is about the second factor, which is the flooring. So we will mention that the flooring is not significant or to the distance of the AGV travel. Okay, lastly, okay, the interaction effect. So it is mentioned that there is no interaction effect between the stripping and the flooring. So this is the three null hypotheses that we have, and three alternate hypotheses is just the opposite, yeah, the opposite for the null hypothesis. So if you mention that over here, you mentioned that stripping is not significant. So your null hypothesis, you will mention that stripping is significant to the distance of the AGV traveled. Okay, over here, if you mention that flooring is not significant, then over here, you will mention that flooring is significant, okay, to the distance of the AGV travel. Okay, so if over here, now hypothesis, you mentioned that there is no interaction effect between the two factors. So your alternate hypothesis, you will be there is a interaction effect between the two factors, which is the stripping and the flooring. Okay, so let us look at how we can do this in JUMP. Okay, right. So we open the data set, open, two-way ANOVA example. Okay, you see now we have two factors. Yeah, we have the stripping and we have the flooring. So what should we do? First, you click analyze. Okay, so now it's not distribution, not fit y by x, we fit model. Okay, we fit model. Remember, the blue color always belongs to y. Okay, then the red color, stripping and flooring. Okay, you highlight both. Highlight both, yeah. Then you click this macro. Then you choose the full factorial. This is the easiest way. Okay, highlight both, you choose full factorial, you will get this stripping, flooring, stripping, flooring. So this is your first hypothesis, second hypothesis, the third hypothesis, you see? Okay, but you also have other option. Okay, you can click on the stripping, click add, you click on the flooring, you add, you highlight both, and then you cross. You will get the same formula like what you did just now, the full factorial. Okay, you highlight both, macro, full factorial, you will get the three functions. Okay, then you just click run button. You will get your analysis over here. Okay, so we look at this in proper writing. Okay, the screenshot for your future reference, yeah. Okay, first we will look at the overall p-value. Okay, the overall p-value is smaller than 0.05, so it means that it's significant lah. Okay, significant, it means that we can proceed to look at the effect test table. Okay, we can proceed to look at the effect test table. Okay, so just now we have formed the three equation, right? The three functions. So first one is the stripping. Okay, so for stripping, okay, so the p-value is greater than 0.05, you see, so we cannot reject the null hypothesis. There's one question, 0.0056 is bigger. No, it is smaller, 0.05 versus 0.005. So it's much more smaller than 0.05. Actually, you can look at the colors in JUMP. You can look at the colors. If it is black, then reject. It's okay. Okay, if it's black, then it's not significant. If it is other colors like orange or red, then it is significant. Okay, in JUMP they provide you the colors, but Python you don't have. Okay. All right. So for stripping, it is not significant. Okay, meaning to say the stripping is not significant to the distance. Yeah. All right. Then we look at the flooring. Whether the flooring is significant or not. Okay, the flooring is significant. Okay, because it is smaller than 0.05. Okay, and lastly, the interaction effect. Is there any interaction effect between the stripping and flooring? Okay, the answer is yes, there is a interaction effect between the stripping and flooring because you reject null hypothesis. Okay, so we agree with the alternate hypothesis, meaning to say there is an interaction effect between the stripping and flooring. So the final conclusion is, okay, we have the stripping, okay, is not significant to the distance of the vehicle travel. Okay, flooring is significant to the distance of the vehicle travel. And there is an interaction effect between the stripping and the flooring. Okay, so this is our conclusion. All right. So that's it about the two-way ANOVA test. So far you have any questions that you want to ask before we proceed to this exercise, and then we proceed to the break.
Doctor, can
Yep.
it more than 3 categories, like maybe 4, 5?
You mean the factor, is it?
Yes, I mean the factor. Yeah.
Okay. So actually for this module we cover up to 2, but in JUMP you can actually dump in any as much factor that as you want. The one we call it as a MANOVA test. It's not two-way ANOVA, it's a multi ANOVA test. MANOVA test, but the one is too complicated. I mean to be covered in this due to the time constraint, so we don't. But in the JUMP tools, the steps are the same. You just dump in, you highlight, if let's say you have 3 factor, you highlight the 3 factor, then you click on the the full factorial, then the formula will be there. So you compare one by one each line, then you will get the same conclusion, like whether you want to accept or reject for each factor. Okay, so for jump tools, the steps are the same for 2, 3, 4 until n factors. Okay. So
Okay. Thanks.
that is for manual tests. Thank you. All right. So you might want to read this quickly. Okay, then I will summarize these for you. Okay, for this example, we have two factors, which is the gender and also the treatment. Okay, we want to see if the treatment and also the gender, whether it will affect the time to relieve pain or not. So we have two factors. First is we will form our null and alternate hypothesis. The first factor, the first null hypothesis is regarding the first factor. The second hypothesis is regarding the second factor, and the third hypothesis is about the interaction effect of the gender and also the treatment. Okay, so you look at this example. This is try this number 3. Okay, so we have the gender, treatment, and the time to relieve pain. Okay, so the same step, analyze distribution, fit model, not distribution, yeah, fit model. Okay, remember the blue color always belongs to Y. Then you highlight the red color. Okay, then you go macro, you choose full factorial. Then it will form the equation for you. The first one is the first hypothesis, second hypothesis, and then finally you have the third hypothesis. Okay, then you click the run button, go down, you will get your p-value over here. First, we will look at the overall p-value. Okay, so this is your overall p-value, which is smaller than 0.05, so it means that we can proceed to look at the effect test table. Okay, so the gender, okay, is significant because it's smaller than 0.05, so we reject the null hypothesis. Okay, we reject the null hypothesis, it means that it is significant. Okay, significant, so which means gender is significant to the time to relieve pain. Okay, then we look at the treatment. Okay, the treatment is also significant, you see? So it means the treatment is also significant. Okay, the treatment is also significant to the time to relieve pain. And finally, we want to see if there is any interaction effect or not between the two factors, which is the gender and also the treatment. Okay, the gender and also the treatment. So it is not significant. Okay, so which means that there is no interaction effect between gender and treatment. Okay, so we conclude that the gender is significant to the time to relieve pain. The treatment is significant to the time to relieve pain. And there is no interaction effect between the two factors, which is the gender and also the treatment. So this is our conclusion. Okay. Okay, so we have 3 more tests where we were going to uh, go through that after the break. So far, you have any questions that you want to ask before we go to the break?
Doctor, like this
Yep.
one means gender and treatment have significant effect, right? So if we want to further know which gender have the greater effect, then we need to perform
Reverse
t-test
back.
for each.
Yep.
Oh,
Yes.
so we need to
For the
perform 2
gender.
times lah to find the gender and also the treatment.
Yep. To see which one is the significant one.
Okay.
Because we have 2 factor. Okay. Thank you. Okay. So no more questions. Okay. If no more questions, then we will proceed to a quick break. Okay. Then we will resume by 2 p.m. Okay. Thank you and see you later. Hey, hello, good day everyone. Welcome back. We have 26 now. 4 more to go. Okay, maybe wait for 1 or 2 minutes for our friends. Okay, then we shall start the session. Thank you. All right, I think we have good number to start now. Okay, again, good afternoon, everyone. Welcome back. All right, so we will proceed to the following statistical test, okay, which is the correlation test. Okay. So we will use the correlation test when you have both continuous variable. Still remember just now we talked about ANOVA test, t-test, you will need to have one blue and one red, right? Meaning to say you need to have one continuous variable and then one nominal variable or categorical variable. Okay, but then now if let's say we have both continuous variable, okay, then we shall use correlation test. Okay, meaning to say you have both blue color. Okay, so the null and alternate hypothesis. Okay, null and alternate hypothesis for correlation test is kind of fixed. Okay, for this one. Okay, we stick to this one. So for example, null hypothesis, it means that it is no relationship between the two variables. While alternate hypothesis, it means there is a relationship between the two variables. Okay, so we have a null and the alternate hypothesis. Okay, so this is for the correlation test. Okay, correlation test is to use when you want to know whether there is any relationship between the two variables. And the two variables, both of them are continuous variable. This is one example. Okay, so when you say there is a relationship between the two variables, how well or how good is the relationship between the two variables? Okay, we will refer to the correlation coefficient. Okay, so if let's say you have 0, it means that there is no correlation between the two variables. If you have 1, so meaning to say you have a perfect positive correlation. If you have -1, it means that you have a perfect negative correlation. And if you have negative 0.5, it means that you have moderate negative correlation. And if you have 0.5, it means that you have a moderate positive correlation. Okay, so when you say there is a relationship between the two variables, how well is the relationship? Refer to the correlation coefficient. So this is how the scatter plot looks like. Okay, remember when we have both continuous variable, both number, okay, we will plot a scatter plot. Okay, we will plot a scatter chart, okay, or a scatter plot. All right. So if let's say you have a chart looks like this, so it means you will have a negative, okay, negative correlated relationship between the two variables. Okay, strong negative relationship. Okay, you have something like this, the scatter plot, so you have a negative moderate relationship between the two variables. Okay, if you have something like this, your scatter plot, the trend, so it means that you have a perfect positive correlation between the two variable. And you have something like this, it means that you have a weak, okay, relationship between the two variables. And you have a flat line, it means that there is no relationship between the two variables. Okay, flat line, it means there is no relationship between the two variables. Okay, for example, if let's say you want to know, is there any relationship between the height and the weight of 20 students? Okay, you want to know if there's any relationship between the height and the weight of 20 students. So height and weight, both of them are continuous variable, meaning to say both of them are numbers. So we're going to do the correlation test. So how do we do this in JUMP? Okay, so we open the correlation test example. All right. Okay. So we will proceed to do the correlation test, yeah? Okay, for correlation test, using you have both, what do you say, the blue color. Okay, both blue color. Okay, so analyze, multivariate, multivariate. Okay. Okay, so you put in both height and the weight, you highlight both. Okay, you highlight both. Okay, then you click on the Y variable. All right, click OK. Not yet, yeah, not yet. Okay, you choose the red color triangle. Pairwise correlation. Okay, pairwise correlation. Click. Then you will get your p-value over here and your correlation coefficient over here. Okay, so based on this example, okay, based on this example, this is the screenshot for your future reference. Okay, first you will need to set your own null and alternate hypothesis. Okay, the tools will not able to do it for you. You yourself as a data scientist or data analyst, okay, will need to do the correlation test. Will need to set up your own null and alternate hypothesis. Okay, so this is the standard template for your correlation test. Okay, null hypothesis, there's no relationship between the two variable. Alternate hypothesis, there is a relationship between the two variable. Okay, so you have null and alternate hypothesis. And we look at the p-value, you see the p-value over here is smaller than 0.05. Again, division rules. Okay, we have smaller than 0.05, we have to reject the null hypothesis. Okay, we have to reject the null hypothesis. Okay, so it means that it is significant. Okay, significant. So it means that there is a relationship between the two variable, which is the height and the weight. Okay, so when you say there is a relationship between the two variable, which is the height and the weight, how well or how good is the relationship between the two variable? Refer to the correlation coefficient. Okay, so correlation coefficient is 0.92. It means that it's a strong positive relationship between the two variables. Okay, which is the height and the weight. Okay, so for this is one example for the correlation test. Okay, now it's your turn to try this exercise. Okay, for a few minutes. Okay, to see whether you manage to derive the right conclusion. Okay, so there's one question. Oh, okay. Yeah, good. Thanks for reminding me. Okay, so for this example, I just want to show you how to import the data table from Excel file, because previously I have already copy paste it to data table to you, so you just open it, right? But if let's say you have an Excel file you want to pump it into Jump, then you can do so. Then you click open, the same step. Okay, open. Then over here you change to all files. Change to all files, yeah. Then you can see all the Excel file, etc., over here. Okay. Then you choose your try list number 4 and you click open. Okay. So over here you can actually for Jump they have the function for you to adjust accordingly. Okay. For example, this the headers, when do you want to start this as your header, and then which column then you want to start as your data. For example, you have 100 row, but you want to start from row number 10 to 20. Then you can set over here. You see, and your data start on which column. For example, you want to ignore the first two row, first two column, then continue for the rest. Then you can use this function. Okay, but for now, ours one is good, so we just import. Then you were able to get this data in. Okay, so we just do a quick experiment. Okay, analyze. Welcome. Okay, analyze multivariate methods, multivariate. Okay, so you pump both in. Y, and then you click OK. Okay, not yet. Red color triangle. Pairwise correlation. Then you're able to get your p-value and your correlation matrix. Okay, let me put in proper writing for you. Okay, so this is the standard template for correlation tests. All right. So null hypothesis. Okay, there is no relationship between the two variable. Alternate hypothesis. There is a relationship between the two variable. Okay, so you run the test and you got the p-value 0.001, which means that it's smaller than 0.05. So in that case, we have to reject the null hypothesis. So it means that there is a relationship between the two variable. Okay, so when you say there is a relationship between the two variable, how well is the relationship? Refer to the correlation coefficient. Okay, so the correlation coefficient is 0.96, which means that it's a strong positive correlation between the two variable, normal and hyperbola. Okay, so this is for the correlation test. Okay, I think correlation test is quite straightforward. Okay, we just want to see if there's any relationship between the two variables. Okay, so far you have any question before we proceed to the regression test?
Doctor, I have a question, Doctor.
Yes. Yes.
Okay, between -1 and -0.01, which one is the weakest relation?
-1 and
-1 and -0.01.
one is the you can see from here, one is the strong negative correlation. You see? So if just now you say negative or positive, negative 0.01 is over
Yeah,
here. So
I
it's
mean
actually
the
a weak
weakest,
negative.
the weakest one is near.
Weakest one is perfect negative correlation is -1. So you compare to negative 0.01 is over here. So which is a weak negative correlation.
Okay, okay, right.
All right, thank you. So if a 0, so it means that there is no correlation. Okay. Okay, so if no questions, then we proceed to the regression test. Okay, we will also use regression tests when you have both continuous variable, meaning to say both numbers. Okay, both numbers, then you will use regression test. So popular question from the floor is, okay, if I have two continuous variable, both numbers, two blue color, which one I should use? I should use correlation test or I should use regression test. Okay, so the main difference between the correlation test and the regression test is there are a few main different, yeah, main different. So for the correlation test is the simpler one, simpler version, where we just want to see if there's any relationship between the two variable, just that. Okay, so you can notice that the scatter plot that we plot, yeah, over here for the correlation test, okay, we don't draw any line, we just want to see the patterns, you see. I just want to see whether how it's spread, and then it's a strong relationship or it's a weak relationship, just that. Okay, but for the regression test, okay, it enable you to do some simple forecast. Okay, and for regression test, the task is to find a best fit, okay, a best fit to represent your scatter plot. Okay, to represent your scatter plot. For example, this case, you see, your scatter plot, you will find a best line, a best fit to represent your scatter plot. Okay, to represent your scatter plot, you will find a line. So that line will enable you to do the simple forecast in the future. So you can use the line to predict, to forecast something. Okay, to forecast something. So this is the first difference between the correlation test and the regression test. Okay, second, for correlation tests, okay, your x and y can be simply switched. You'll get the same conclusion. Your x can be your y can be your x. You can be height versus weight or weight versus height is the same. you will get the same conclusion, okay, the same p-value, the same correlation coefficient. Okay, so both are the same. There's no dependent variable or independent variable. But for your regression test, you cannot simply change the sequence of your x and y. Your x is your x and your y is your y. Okay, if you change this two variable, then you will get different results. Okay, and also different p-value. Okay, everything will be different. Okay, their patterns will be different as well. So for regression tests, you need to define properly which one is your x and which one is your y. Okay, your y is your dependent variable, okay, and your x is your independent variable. Independent variable, it means it doesn't depend on anyone. Okay, but y is the dependent variable. It means it depends on the value of x. For example, your your book sold, the number of books sold. The number of books sold is depends on the number of student registered in that semester. Okay, so the student registered in that number of student registered in the semester, that is the independent variable because it doesn't depend on anyone. Okay, the number of students registered. Okay, while for the number of books sold, it depends on the value of the number of student registered. Okay, so it depends. So it's dependent variable. Okay, so you have independent variable and you have dependent variable. Okay, so for the second difference, okay, is the correlation test. You can simply switch the position between the x and y, and regression test you can't. Okay, and one last main difference is correlation test you cannot do any forecast. Okay, but for regression tests, you can do simple forecast, okay, based on the results. Okay, so that's the main difference between the correlation test and regression test. Although both of the tests, statistical tests, they requires the continuous variable. So when you have both continuous variable and you want to decide, okay, whether you want to use correlation or regression, so you need to refer back to your objective. What is your objective? You just want a simple analysis, or you want something, you know, complicated, or more advanced and something. Okay, so that is the main difference. All right, so for regression, okay, we have linear regression and then we have multiple regression. Okay, so again, the null and alternate hypothesis for the regression test is kind of fixed, okay, for this experiment. Okay, null hypothesis, the slope equals to 0, meaning there is no slope, meaning to say there's no relationship between the two variables. Still remember, if you have a flat line, it means there is no relationship between the two variables. Okay, H1, okay, the slope is not equals to 0, so it means that there is a relationship between the two variables. Okay, so we will use linear regression when you have only one independent variable and one dependent variable. Okay, 1 to 1, then you use linear regression. If you have one to many, you have many independent variable, more than one, then we use the multiple regression. Okay, more than one independent variable, we use multiple regression. Okay, so this one I've already explained just now. Okay, you have one to one, then you use linear regression. So this is how the scatter plot looks like. Okay, you have something like this, so it means that it's a strong positive relationship. If you have something looks like this, so it's a weak positive relationship. And then this one is a negative strong relationship, and then negative weak relationship. Okay. Then if you have a flat line, it means that there is no relationship between the two variables, x and y. Okay, so this is the equation for the linear regression, where I believe all of us are very familiar with this already. Okay, y equals to mx plus c. Okay, this is what we have learned previously. Remember, maybe in our secondary school or during our degree time. Okay, y equals to mx plus c. Okay, just this one is a different notation that we use. Y equals to mx plus c. Okay, so this is the equation for your regression model. Okay, so this is how a scatter plot looks like. Okay, when you have both continuous variable, for example, house price versus square feet, the size of your house. Okay, so you have both continuous variable. So this is you will need to plot a scatter plot. So for jump, okay, for jump tools, for linear regression, they will output this linear regression equation for you. Okay, this equation they will give it to you for linear regression. Okay, so this equation will enable you to do a simple forecast later. Okay, for jump it will give you this equation, but for other statistical tools you might want to, you know, collect all of these items and then put it into your regression equation. Actually, all these numbers they have derived from here. You see the number are from here, but just that for for jump, for linear regression, they will give you the equation right away. Okay, so you can just use this equation for the simple forecast later. Okay, so when we talk about the equation y equals to mx plus c, y is the house price. Okay, and then you have your x, which is your square feet. Okay, so your plus c, right? The c is the intersection point of your best fit, and then your m is your slope. Okay, is the slope of your best fit. So you have y equals to mx plus c. So what does it mean by the equation? When you got an equation, of course, there's a certain meaning, on your equation. Okay, so how to interpret your equation? Okay, y equals to mx plus c. Okay, so this means when your house price increase, okay, when your house price increase, sorry, when your square feet increase by 1 unit, okay, your house price will also increase by 0.10977. Okay, so it means that when your square feet, which is your x, yeah, when your x increase by 1 unit, your house price will increase by 0.10977. Meaning to say, if your house is bigger, then your house price will be bigger, will be higher lah. Okay, because this one is unit wise, so it will be when your house increase by 1 square feet, then it will increase by your house price will increase by 109 ringgit. Okay, so this is the meaning for this equation. All right. So by using the equation, you can do a simple forecast. Okay, if let's say you want to forecast a price for a house with 2,000 square feet, you just replace the value in. This is the equation provided by Jump to you. So you just drop in the value 2,000 square feet. So you put it over here. Okay, then you sometimes etc. etc. Then you get a house price 317.78. Okay, so which means if you have a house 2,000 square feet, your house price will be around 317,789 ringgit. Okay, so you can make a simple forecast by using the equation, okay, the equation provided by the by Jump to you. Okay, so when you say there is a relationship between the two variable, okay, because over here we have mentioned that there is a relationship between the house price and the square feet. So how well is the relationship of the house price and the square feet? Okay, refer to the R squared value. Okay, refer to the R squared value. John will output the R squared value for you. Okay, so this R squared value, okay, so this R squared value will let you know, okay, how well is the relationship between the two variable. For example, this case, okay, we mentioned that there is a relationship between the house price and the square feet. How well is the relationship between the house price and the square feet? Refer to the R squared value, you will get 0.58, meaning to say 58.1% of the variation in the house price is explained by the variation in the square feet. So it means that it's a moderate relationship between the two variables, not really strong, of course, because common sense, we know that house price not only depends on the size of the house, right? But it also depends on other factors like the location, etc., etc. Okay, so for this case, how well is the relationship is 58.1%. All right. All right, so let's look at the example to see how we can do this by using jump. Let me open the linear regression example. Click open. We have the price and the square feet. Okay, so first we will click analyze. Then you will go to fit y by x. Okay, so previously we put the blue color to y, right? And then red color to x, but now we only have blue. Okay, because regression test we use when we have both blue color, which is both continuous variable. So y is your dependent variable. Okay, we need to remember y is your dependent variable while x is your independent variable. Okay, so dependent variable is the price because the price depends on the square feet, right? So price is your dependent variable, y, then x square feet independent variable. Square feet it doesn't depends on anyone, so it's your independent variable. Okay, then you click OK. All right, so not yet, yeah. Click on the red color triangle. Click fit line. Okay, then you will get your p-value over here. Okay, let's look at this in the proper writing. Okay, so as you can see, jump will output this equation for you. Okay, the equation for you. All right, y equals to mx plus c, and then you can use this for your forecast later. Okay, then when you okay, so we look at the p-value first. Okay, we look at the p-value. So p-value is smaller than 0.05, so we have to reject the null hypothesis. So we reject the null hypothesis. Okay, okay, wait, yeah. All right, so we use if because the p-value is smaller than 0.05, so we reject the null hypothesis. Okay, we reject the null hypothesis, so it means that there is a relationship between the two variables. Slope is not equals to 0. Okay, slope not equals to 0, so it means that there is a relationship between the two variables. Okay, when you say there is a relationship between the two variables, how well is the relationship? Refer to the R squared value. Okay, refer to the R squared value. So we can see that the R squared value is 58%. So it means that 58.1% of the variation in the house price is explained by the variation in square feet. Okay, so it's a moderate relationship between the two variables. Okay, so conclusion, okay, we can conclude that okay, the house price okay, will be affected by the square feet. Okay, so there's one question over here. Can use date for regression tests? It depends on the objective. What do you what I mean, what is your main objective? So usually we won't because it's to me it doesn't mean I mean it doesn't have much motivation, I would say. And then the purpose of doing this is also need to be clear lah. Unless you have a specific objective, then we can use, but unlikely we will use this for the dates. Because when you talk about date, then the first thing that I will recommend to you is the time series time series experiment. So you can just do a simple time series experiment, then you can get more accurate and then more informative results, okay, compared to regression tests. Okay, so it depends on your objective, like what do you want to apply, and then what is your motivation of that. All right. Okay, so This is the screenshot for your future reference. Okay, so let's try this. Okay, try this exercise. Okay, then we see whether you manage to find or you manage to detect, okay, what is the number of books sold if there is 50 student register. Okay, so let us look at this example. Try this number 5. All right. Open. Try this number 5. Okay, we click open. All right. Okay, so we click analyze. Okay, fit y by x. Okay, the dependent variable we put at the y, number of books sold. It depends on the number of student register. Okay, so we click OK. You click the red color triangle and you fit the line. Okay, then you will get your p-value and your equation, etc., etc. Okay, so we put improper writing. Okay, so this is the null and alternate hypothesis for the regression test. Okay, for null hypothesis, okay, there is a relationship between the two, there's no relationship between the two variable. Alternate hypothesis, there is a relationship between the two variables. Okay, so we look at the p-value and we notice that the p-value is smaller than 0.01. So it means there is a relationship between the two variable, which is the number of student register and the number of books sold. Okay, so when you say there is a relationship between the two variable, how well is the relationship? Okay, we refer to the R-squared value. Okay, the R-squared value is 80.9%. So it means that it's a strong relationship between the two variable. Okay, so at 80.9% of the variation in the dependent variable is explained by the variation of the independent variable. Okay, so we can conclude that there is a relationship between the two variables, which is the number of books sold and also the number of student register. Okay, so now we use this equation, okay, to perform a simple forecast. If let's say we have 50 student register, you just pump into the equation, then you can forecast around 43 books, okay, will be sold. Okay, so they can prepare accordingly lah, the number of books, okay, for the students. Okay, so this is the linear regression example. Okay, so far you have any question before we proceed to the multiple regression? Okay, all right, so if there's no questions, okay, on the regression, linear regression, we will proceed to the multiple regression. Okay, for multiple regression, we will use it when you have more than one independent variable. Just now, we only have y equals to mx plus c, right? But now you have many mx, m1, x1, m2, x2, m3, x3 until n, mn, xn. Meaning to say you have many independent variable instead of only one independent variable. Okay, so this is an example. If you have your dependent variable, which is your pie sales, and your independent variable, you have price and the advertising cost. And you have a price and your advertising cost. So you have two independent variable and you have only one dependent variable. So for this case, we were going to use the multiple regression. Okay, we're going to use the multiple regression. So this is the equation that we have. Dependent variable sales depends on mx. The first x is the price, second x is the advertising cost. Okay, y equals to m1, x1, m2, x2 plus c. Okay, so for the multiple regression in JUMP, they don't provide you the equation, okay, the ready equation. Okay, because imagine if you have many variable, okay, then it will be not nice for them to show you or list out the equation. You see, so for multiple regression, we can form our own equation to perform the simple forecast. Same goes to the linear regression. Actually, the values are there. We just want to pick it up and then use it. Okay, but for multiple regression, we also can do the same thing. Okay, y equals to mx plus c. So your first x is your price, your second x is your advertising cost. Yeah. So the price, okay, the price over here you can see over here price. This is your price punya value, your M1. M1 is negative 24.97. And then your advertising cost, what is the M? The slope is 74.13%, 74.13. So 74.13, you put it over here. And what is your interception point? Okay, interception point over here, 306.52. 306.52. Okay, so this is the interception point. Okay, so this is your equation. You have formed your own equation. Okay, so what is the meaning of this equation? Y equals to M on x1, m2, x2 plus c. Okay, so your y is your dependent variable and your x is your independent variable. So you have a dependent variable and then you have the independent variable. Okay, so what is the meaning of the equation? All right, so the meaning of this equation is for M1, okay, it means, let me open the pen. Okay, so this one, it means if your price increase by 1 unit, your sales will drop by 24.975. Okay, well, for advertising costs, if you increase your advertising cost for 1 unit, your sales, okay, your sales will increase by 74.131. So it means if your price of your pie increase, then your sales will drop. I mean, this one is normal lah. If you sell in the higher price, then your sales will drop. Okay. While if you advertising more, if you advertise more, you spend more money to advertise your pie, then your sales will increase by 74.131. So you will increase your sales if let's say you increase the advertising cost. Okay, so this is the meaning of your equation, yeah? And by using the equation, you can do the simple forecast. Okay, you can do the simple forecast. Yeah. So by you can do simple forecast and just pump in the equation to the equation. If let's say you want to sell your pie at the 5.5 ringgit and you want to use 350 ringgit to do advertising, okay, you can pump into your equation and you get your sales, which is 428.62 pi. So your forecast sales will be around 428 or 429 pies. Okay. So when we say there is a relationship between the two variable or the three variable, how well is the relationship? We will refer to the R squared value, right? But the R squared value is only for the linear regression, because for the multiple regression, when you add in more variable, you have more x, right? X1, X2, X3. When you add in more variable, you will lose a degree of freedom. Okay, so this means that we will need to adjust the R squared value, okay, so that the bias can be excluded. Okay, so when we say there is a relationship between the variable, the independent and the dependent variable, how well is the independent variable is being explained by the dependent variable, refer to the adjusted R squared value. For linear regression, we refer to the first one, the R squared value. But for the multiple regression, we refer to the adjusted R squared value. Okay? So adjusted R squared value is 44.17%. So this means that 44.17% of the variation in pie sales is explained by the variation in the price and advertising. Okay, so meaning to say 44.17% of the dependent variable is being explained by the independent variable. Okay, so not a very strong relationship between the dependent and the independent variable. Okay, so let's try how we can do this in JUMP for multiple regression. Okay, for the multiple regression. Okay, let's open the data set. Multiple regression example. Okay, so we have the dependent variable and then you have the independent variable. Okay, so first analyze fit model. Okay, we use fit model, yeah, instead of the fit y by x or the distribution. Okay, so you put in your dependent variable, yeah. Again, you put in your dependent variable over here, y. Your y is your dependent variable. Okay, and then the remaining independent variable, you just add in. Don't use the full factorial, yeah. Full factorial is only for the ANOVA test. Okay, for the multiple regression, okay, we use this add. We just add in this to our x. Okay, so you have pi sales as your y, the remaining two as your x. Okay, then you just run, and you will get your p-value and also your equations value here. Okay, so let me put in a proper writing for you. Okay, so from here, okay, we can, okay, so before this, we need to shape our null and alternate hypothesis, yeah? Null hypothesis, it means that there is no relationship between the dependent variable and also the independent variable. Okay, while for alternate hypothesis, okay, there is a relationship between the two variables. Okay, the dependent and the independent variable. Okay, so we look at the overall p-value. Okay, overall p-value is 0.012, which is smaller than 0.05. Okay, when we say it is smaller than 0.05, this means that we reject the null hypothesis. Okay, we reject the null hypothesis. Okay, when we say we reject the null hypothesis, so we can conclude that there is a relationship between the dependent variable and also the independent variable. Okay, so which variable is significant to the dependent variable? Okay, we look at the parameter estimate table. Okay, so for the price, okay, you look at the p-value. Smaller than 0.05, it means that it is significant. So it means that price is significant to the pie sales. Okay, so meaning to say the price will affect the pie sales. There is a relationship between the price and the pie sales. Then we look at the advertising cost. Again, it is significant. So it means that there is a relationship between the two variables as well, which is the advertising cost and the pie sales. Okay. So in conclusion, okay, we conclude that okay, we have sufficient evidence saying that the pie sales, okay, will be affected by the price and the advertising cost. Okay, so this is our conclusion for the multiple regression. Okay, so this the screenshot is for your future reference. Okay. All right. So far you have any questions that you want to ask for multiple regression before we proceed to the last test, which is the chi-square test.
Doctor, for the H alternative for multiple regression, would be just now beta 1 and beta 2 is not equal to 0, right? So is there any case that the answer is beta 1 equal to 0, beta 2 is not equal to 0?
Yeah, so for this case, we will need to refer to this one. Yeah, they might, if let's say you have many independent variable, there might be some case where certain of them is not significant. So if that's the case, then usually what we do is we drop the few variable, okay, that is not significant, then we rerun the model. We run until all of them are significant, then only we use the equation to do the forecast. Else is not significant, then the forecast will not be accurate as well. Okay?
Okay, thank you.
Yeah, thank you. All right, so we proceed to the last test, which is the chi-square test. Okay, we will use the chi-square test when we have both categorical variable. Okay, when we have both categorical variable, which means both category, then we will use the chi-square test. All right. So again, the null and alternate hypothesis is kind of fixed for the chi-square test. Okay, null hypothesis, it means that there's no relationship between the two variable, and alternate hypothesis, there is a relationship between the two variable. So this is just for your information, no need to memorize. Okay, just to let you know, we use the chi-square statistic for this analysis. Okay, so let's look at this example. Okay, if let's say we want to know whether there's any relationship between the colors versus the personality. Okay, the colors versus the personality. If there's any relationship between the two variable, okay, you can see colors are categorical variable. Okay, they are in category. Personality also is a categorical variable. You have introvert and extrovert. Okay, so both categorical variable, we will use the chi-square test. Okay, so let's see how we can do this in JUMP. So we open our JUMP tools and open the last example, chi-square example. All right. So for chi-square example, so we click analyze, okay, then fit y by x. Okay, analyze, fit y by x. Okay, so you put in the factor for chi-square test, you can use either. They are fine. There's no sequence. Okay, you can put in colors, personality as your x or y. You will get the same conclusion. Okay, you will get the same conclusion. Then we click OK. You see? So you will get your p-value down here. All right. So let me put in proper writing for you. Okay, this is for your future reference, the screenshot. Okay. So now hypothesis. Okay, now hypothesis, there is no relationship between the two variable, which is the color and the personality. Okay, while alternate hypothesis, there is a relationship between the two variable, which is the color and also the personality. All right. So we refer to the p-value. Okay, your p-value over here. Okay, so p-value is smaller than 0.05, so we reject the null hypothesis, which means there is a relationship between the two variable, okay, which is the color and also the personality. And if you observe the multi-plot, you can see that actually extrovert, they prefer red rather than introvert, while introvert actually they prefer blue color compared to extrovert. Okay, so this is the final conclusion that we get from the chi-square test. Okay. So maybe you want to have a quick try for this example. Okay, to see whether you can get the same conclusion. Okay, with mine later. Okay, so you might want to try. Okay, thanks for sharing your answer. A few of your friends have shared the answer with me. All right, so let's look at the quick analysis. All right, so the last example, try this 8. Okay, so for this example, we want to see if you see we have both rate, yeah? Both rate meaning both categorical variable. So we are going to do the chi-square test. Yeah, we're going to do the chi-square test. All right, so analyze fit y by x. Okay, you want to see if the qualification has any relationship with the marital status. Okay, so we simply put the sequence is fine, right? Click OK. So you can see from here the p-value. Okay, so it is not significant, yeah, because it is greater than 0.05. Okay, so null hypothesis, there is no relationship between the two variable. Alternate hypothesis, there is a relationship between the two variable. So when the p-value is greater than 0.05, so we can say that we cannot reject the null hypothesis. So meaning to say there is no relationship between the qualification versus the marital status. Okay. Okay, I received another questions. For the p-value. For p-value, which one that you should refer to? Actually, we refer to the Pearson one because we are using the Pearson correlation. So we are referring to the Pearson one. The difference between these two actually is one, they are using ratio, which is the Pearson relationships, while the other, which is the likelihood relationship. And the Pearson one, they are using the difference, okay, the difference between the two variable. So normally or basically we will use the Pearson relationship. Okay, so usually you will have the same p-value. So if let's say reject, then both will be reject. If let's say accept, both will be accepted. It's very unlikely that you will get the different results. Okay, unless you have a very dirty data set, then you might run into that issues. Okay, but usually you will get the same one, and we will refer to the Pearson relation. Okay, thank you. All right, so you have any questions that you want to ask before we play a quick game, a Quizlet game? If let's say you have no questions, then please go to the Quizlet, Quizlet. Okay, then I will launch the game. Okay, so please join the game. You can scan the QR code, then you can join the session. Okay, so congratulations to our champion for today. We have Aini, okay, as our champion for today. Okay, congratulations. You have very super fast. Yeah, super fast because I think you have break the record from the previous cohort. Yeah, you have answered all the questions correctly. Okay, for all the 12 questions. Congratulations. Okay, very good job and very well done. Okay, congratulations again to our friends Aini. All right, so I hope you enjoy the game. Okay, and I hope that you really gain something from the game. Okay, so so far you have any questions before? Okay, so far you have any questions before we proceed to the break? Okay, the afternoon break. Okay, so if no questions, then we will proceed to a quick break. Okay, and we will resume after 20 minutes. Thank you, everyone. Hello everyone, welcome back. So I think we are a good number to proceed. Okay, so just a quick revisit, yeah, for what we have learned in these 2 days. Okay, so we have learned about all the statistical techniques, okay, for CDA. Okay, so let me remind you again. Okay, for t-test, we will use one sample t-test when you have only one group. Okay, you want to see whether it is equals to, greater than, or smaller than a specific value. Then you use one sample t-test. Okay, while you will use two sample t-tests when you have two groups. And if the two groups are dependent, okay, there's a relationship between each other, then you will use the pair sample t-test. Okay, while if the two groups are independent, meaning there's no relationship between each other, then we will use the independent sample t-test. Okay, so if you have more than two groups, then we will use one-way ANOVA test. And if you have more than one factor, then we will use two-way ANOVA test. Okay, or for regression and correlation, we will use it when you have both continuous variable. Okay, and linear regression, we will use it when you have only one independent variable. Or if you have more than one independent variable, we will use multiple regression. Okay, for classical test, we will use it when we have both categorical variable. Okay, so remember the main subcomponent under commonality analysis is the EDA and CDA. Okay, where you have learned all the small components under these two big topics. Okay, and remember the space shuttle challenger that we have mentioned before, the case study, okay, which have taught us that we will need to include both good and the bad sample when we perform data analysis or data analytics. Okay, and commonality analysis, okay, is the characteristic of the bad lots, and it happens because of something. Okay, it won't happen randomly. Okay, it must be triggered by something. Then you will need to find out the signal, solve it, and bring the process back to normal. Okay, so these are the goals for the commonality analysis that we have learned last week. Okay, the main goal, the ultimate goal is to find out the root cause, solve it, and bring the process back to normal. Okay, and remember for commonality analysis, okay, it is sequential nature, which means you don't need to have a very rich data set or a perfect data set at the first place. We use whatever that we have in our hand first to conduct the analysis, okay, and we see how it goes. Okay, if it is not sufficient, then we top up, okay, and the process will go again. All right. So at the last place of the session, okay, I would like to show it to you, or maybe to demo to you how we can apply all this knowledge that we have learned, the small theoretical and hands-on parts that we have learned, okay, and apply it to a real world example. Okay, so for the first example, okay, so for this example, they actually found out that there is a high bin loss, okay, high bin loss in this fab, okay, in this fab, and they suspect that it is because of fab, or it's because of vendor, or it's because of the chip attached module. So this one we use the dataset one. It's also in the drive. Here, if let's say in future you want to try to play around with, here you can do so. Okay, so for this dataset, for this data, okay, they suspect either is fab, vendor, or chip attached module. So as I mentioned before, okay, it will be very cost intensive if let's say we want to inspect every of them. Fab, you have two elements, vendor you have three, chip attached module you also have three module. Okay, so it would be very cost extensive if let's say we proceed to investigate all of them. Okay, so we can't. Okay, we can't. So we need to do a commonality analysis so that we get a quick decision, okay, to proceed to which one that is suitable. Okay, so first we will investigate the fab plant. We want to see whether it's because of the fab 12 or fab 15 that actually caused the low yielding lot. Okay, the high bin loss. Okay, so which one? Is it the Fab 12 or the Fab 15? So we plot the date versus the bin loss and according to the Fab plan. So we have two Fab plan, Fab 12 and Fab 15. So which one? Which one is the root cause that actually caused this happen? Okay, if you look at the chart, the scatter plot, you will need to select the right charts here to be plot. Okay, so since we have both continuous variable, we're going to use the scatter plot. Okay, so this is how the scatter plot looks like. And if you can see over here, for the Fab 12 and the Fab 15, actually there are no significant commonality being observed because you can see that high bin loss actually contains of both the Fab 12 and Fab 15. So actually for this case, we don't see any significant signal or commonality signal at the place. You see? So from here, we actually conclude that there is no commonality being observed. So it's not Fab 12 or Fab 15. Both of them produce high bin loss, you see? So no commonality being observed through this EDA process. Okay, so of course, one statement is not sufficient, to the implementation. So we proceed to the CDA, confirmatory data analysis. Okay, so for the confirmatory data analysis, again, you yourself as the data scientist or the data analyst will need to decide what is the statistical test that you want to use. Okay, if you have two groups and there is no relationship between the two groups, they are independent, so we will use the independent sample t-test. Okay, so after you run the test, you look at the p-value. Since this is equal sign, we will refer to the first one, which is the two-tailed test. Okay, 0.34, it means that the p-value is greater than 0.05, so we have to accept the null hypothesis. Okay, so we accept the null hypothesis, which is we accept this one, the null hypothesis, and then we conclude. So it means that there is no significant difference. Okay, we conclude that Fab plan is actually not significant to the high bin loss. Okay, so we can already ignore the first factor, which is the Fab plan. Okay, so you can see that there's no commonality being observed from this first factor. Okay, so moving forward to the second factor, we have vendor. Okay, we have vendor. So for vendor, again, we plot the same charts. Okay, the date versus bin loss. Again, both continuous variable, you will need to plot a scatter plot. So from here, you can actually see that there is a strong commonality being observed from vendor A. Okay, because you see all the high bin loss actually contribute from this vendor A. You see? So from here, okay, you can actually know that vendor A is actually the root cause. Okay, so the engineer should go straight to the point to investigate why this happened because of the vendor A. So what's wrong over there? Okay, so this is for the vendor A. Of course, you will need to support by confirmatory data analysis, your CDA. Okay, so now we have three groups. We have three vendor, vendor A, vendor B, vendor C. So so this is our null hypothesis, vendor A, B, and C. While for alternate hypothesis, not all mu are the same. Okay, so meaning to say meaning to say at least one is different from another. There's one vendor is significant. Okay, so we use the knowledge that we have learned before. If you have more than two groups, okay, we will use the one-way ANOVA test. Okay, so you run the test and you got the p-value over here, which is significant. Okay, significant, so it means that at least one of them, okay, is significant. Either is vendor A, B, or C. So which one is the significant one? We will do the t-test. Okay, we will do the t-test like what we have did just now during the hands-on session. Okay, so we compare one by one. if you compare the mu for A and C, okay, you can notice that it is significant. Okay, so if you compare the mu, okay, for A and B, so you will notice that again it is significant. Okay, significant, it means the mean of this A and C is different. The mean for these A and B are different. And you compare B and C, the value of B and C, not significant. It means that there is no difference between the population mean of B and C. So who is the significant one? The significant one will be vendor A. So vendor A is the significant cause that actually caused the high bean loss. Okay, so now it's already we have another fact to support our findings from EDA where the main root cause is actually vendor A. Next. Okay, lastly, we have the chip attached module. Okay, chip attached module. So for the chip attached module, okay, you can see from here, okay, the high bin loss actually contribute from all the chip attached module. 1, 2, and 3. You see? So we cannot define that, we cannot find the commonality signal over here because all of them contribute the same thing. Okay, so no commonality being observed for this example. Of course, you will need something to support your justification. So we look at this CDA. Again, if you have more than 2 groups, then we will need to use the one-way ANOVA test. Okay, so we look at the p-value. Since the p-value is 0.84, so it means that it is not significant. Not significant, it means that the chip attached module is not significant to the high bin loss. So again, the engineer can just ignore this chip attached module. So this is our conclusion. Where you look at the first factor, okay, there's no commonality being observed, and it has been proven by our EDA and CDA experiment. Okay, next you look at the chip attached module. Okay, again, there's no commonality being observed. Okay, where they have the same population mean. Okay, also it has been supported by both the EDA and the CDA analysis. And lastly, you have the strong commonality observed to vendor A. Okay, we have already noticed that vendor A is actually the root cause for this example. Okay, so that should actually go to investigate, okay, about vendor A that caused the high bin loss. Okay, so throughout the session for this for this module, okay, so we have learned about all these small component. Okay, first day you learn about Python, and for today you have heavy hands-on on jump tools. Okay, so we have learned about all the EDA and the CDA components, and we learn how we combine all of them and apply it to our real-world use cases or the real-world projects. Okay, so I hope that you find the module useful, and I really hope that you can apply this to your real-world data set, meaning to your workplace data, okay, or at least to come up with some insights from there. Okay, so I think you have any questions that you want to ask at this moment before we proceed to the post test? Okay, so if no questions, okay, then we will. Oh yeah, this is a warm reminder from Dr. Halim to do the module assessment. I think you will need to find in a general folder to do the module assessment. Yeah, maybe just a few minutes for you to perform the module assessment. Then we will proceed to the post test. Okay, so yeah, maybe just a quick one. Then later we proceed to the post test. Okay, so now we will move to the post-assessment. Okay, so there will be no more lecture after that. Okay, so once you have complete your post-assessment, then you can leave the session. Okay, so I take this opportunity to wish everyone Selamat Hari Raya in advance. Okay, and yeah, enjoy your Raya later. All right, so now we will proceed to the post-test. Okay, and I wish you all the best. Yeah, I will see you maybe during your final presentation. Okay, so I have launched the post-assessment. You can refresh your e-learning portal and then you can see it under the instruction tab. Okay, so you can do the test and then yeah, after that you can leave the session. Okay, there's no more lecture after that. Thank you everyone and have a good weekend. All the best. So I think I will end the session here. Thank you, everyone. Have a nice day. Bye.